Good morning. Good morning. Thank you very much to be here. Some people is coming. I am checking because we are waiting people. But let me to introduce Concetto is Spampinato. Is a good colleague that we are now collaborating with the people who are working starting with European proposal, and also with collaboration with other colleagues from other university. Concetto is full professor in University of Catania, president of CD and leader of the lab Perceive. As artificial intelligence lab serves and he is, as I told you, the president of the Center for Informatic Digitalization and Artificial Intelligence. He has some high quality number of publications in different areas, like computer vision, foundation model, explainability, continual lifelong learning, and so on. Really, he has a deep and high quality curriculum and number of activity, and really it's an honor, a pleasure for us. His acceptance to be here with the talk today about we will discuss in this case about explainability and understanding as our definition, but from the point of view of the vision models. And remember the question that I did introduce you about to open Catavenici in Nature published a paper 12 years ago with the question, the question of to open the black box, and then it is really we will enjoy with the talk of Concetto about this topic in the vision models. Thank you very much. Please.
Thank you everyone. Thanks for the invitation. I mean, I'm really happy to be here. I've been collaborating with the Granada people since a while, and now we finally meet in person. So today I'm gonna talk about opening the black box. So basically, I will present you our recent works on how to understand and dissect the models by accessing both the model parameters and by using in an extremely black box way without accessing the model parameters. So what I will present is basically the activities that we do in our lab. So I created more than 10 years ago the Perceive lab. At the moment the lab has a few PhD students, several academic professors, and there are three main research groups. The first one is the Cognitive Inspired Learning Group, the Medical and Brain Image Analysis Group, and the Multimodal Learning and Reasoning Group, where there is a sub-team on explainable AI. And here you see the people working on this area. So let's move directly to the talk. So this the agenda of this talk. I split the talk in 4 parts. The first one is foundations. I mean, I'll be presenting, but I'm sure you already know transformers and foundation models and how to adapt foundation models to downstream tasks. Then we will be talking about explainability and the one I called the explainability crisis. And then we'll see the research we do on this topic. So from visual to text explanations, this is our recent work, and then how we move towards causal understanding. Okay, so let's start with the foundations. So we know that in the last, I would say, 5 years, there has been a trend moving towards task-specific models to general purpose models. So at least the not so young people like me, we started by doing feature engineering, then we moved to convolutional neural networks, where we basically learned features that were oriented to address a specific task. And now we are in the era where we have very general AI models, and we try to adapt these general models to specific downstream applications. So the story starts from transformers. So I guess you all know what a transformer is, but I decided to add these slides because we need to understand better how we use the transformer architecture to make our explainability approaches. So we know that in transformers we have this encoder-decoder architecture. And we know that everything starts from the source sequence, then we do some embedding. Then this embedding goes through a set of encoders, a set of encoder layers where we basically learn, let's say, features at different abstraction level. And then in the original formulation, there is also a decoder just to do some autoregressive task. And this architecture I was mentioning earlier. If we go deep and we look at the encoder architecture, we know that we have several layers, and these are the main, let's say, operations done within the encoder. So we have the multi-headed self-attention, and then followed by layer norm feed-forward network, and this goes to the next layer. The key intuition of transformer was the multi-headed self-attention, which also has strong implications on explainability, and we will see in a few minutes. And we know that in the self-attention, these the operations that we basically do, where we have key, query, and value, and we try to transform the input data into a new space. One important thing of transformers is basically that we do analysis on multiple heads. This is quite important because each single head at the end will learn some specific features on our data. So I assume you all know what the heads do. So basically, given the input feature, we just split down the features into multiple heads in a way just to understand what each single feature will represent. This is what basically it is done within the transformer. Given the value, where the value is the image, we just learn some attention weights, which comes from multiplying again the input by itself, and we obtain the output. When we do this at different heads, you can see in this slide that each single head at the end encodes some specific information from the input data. Okay, but I mean, this is just a very generic overview of transformers. We all know that transformers were born initially for text and for time series, but what I'm interested in, and because I was born as a computer vision scientist, the idea is the good thing is that transformer can be also applied to vision task. And this leads us to the VIT model. I guess you all know VIT, right? The VIT model, you know? Okay, in the VIT model, which is what was proposed in 2020, we treat image patches as a sequence. So we basically split down, divide the image into patches, and then each patch becomes a token in the sequence of transformer. In the case of VIT, we use only encoder. We do not use decoder because what we need to know is just to learn some more compact representation from images. Of course, since patches have 2 dimensions, they are flattened in VIT model. And this is the VIT architecture, where basically to do some specific, let's say, classification task. For instance, in the case of the paper, they just added one classification token. The classification token is the token that we basically use to make all our analysis. One of the main advantage of transformer was that transformer led us to the universal architecture. This was extremely important because this allowed the community to combine multimodal data and also data with arbitrary size. This was extremely, I keep saying to my students, this was the most important innovation of transformers, the possibility to have only one architecture for several tasks and for several different modalities. The consequence of this was that after transformer, we have the foundation models. I guess that we all know foundation models, and we know that the foundation model is a large-scale neural network, basically trained on large-scale data in an unsupervised way. Self-training, it is done for creating foundation models. And we know that at the end, foundation models just retain general knowledge. That knowledge needs to be adapted to specific downstream tasks. So here there are 2 points. Generally, the good things is that for creating foundation models, we didn't need to have labeled data, and we used self-supervision. And these foundation models can be adapted to a wide range of downstream tasks. Okay? One of the most significant example, or one of the most important example of foundation models is CLIP, where we basically combine image and text, and we try to do a task which basically combine the two. So in the CLIP model, do you know CLIP, right? All of you? Okay. So in the CLIP model, we have one text encoder, transformer architecture, one image encoder, again, a transformer architecture. And these, of course, as text changes, image changes, we get several different embedding space. The idea of CLIP was to force encoders to have the same representation for the same concept. Okay, and this was trained using contrastive learning. So the idea is we have a bunch of images, a bunch of text corresponding to the images. The images are processed through a transformer image encoder to get some latent representation for images. The same for text. And then these 2 things are put in correlation in this matrix, where the objective is to maximize the diagonal values, okay? Because we want to maximize the similarity between the correct pairs of image and text, okay? The good things of CLIP is that it enabled zero-shot classification. So once it is trained, and it was trained on a huge quantity of data, you can use for zero-shot classification. That means what? That once it is trained, to do the classification, you just provide a list of words to the text encoder, and then one image to the image encoder, and then you measure the similarities. The similarity, the highest similarity will give you the correct label for the image. Okay. So, as I said at the beginning, an important thing of foundation models is that they are trained on a huge quantity of data, and then that can be adapted to specific downstream tasks. So we know that adapting foundation models, there are several strategies to adapt foundation models. Of course, the easiest one, the most straightforward one, is to do fine-tuning, full fine-tuning, okay? Of course, to do full fine-tuning, you need enough data just to change the parameters. One other strategy is to keep everything frozen and just change the last classification or task head. This is called linear probing. And there are also other strategies. One important strategy is VPT. Do you know VPT? Visual Prompt Tuning. So in VPT, basically, you keep everything frozen and you just learn prompts, just some specific tokens that steer the representation of the model towards the specific task. You see the fire icons there. Basically, these things here are the standard input data tokens, and you just add some additional parameters, additional tokens that are optimized to address some specific task. Another strategy, which is the most common one, is by using adapter. The techniques fall under their PEFT category. Have you heard PEFT? Parameter efficient fine-tuning techniques, and one of these is LoRa. I guess that all of you know LoRa's, where you basically learn some additional parameters in a compact way by using an encoder-decoder architecture, and you just sum those additional parameters which are optimized for your specific task to the base representation learned by the foundation models. Okay, this was a very extremely fast overview of transformers, foundation models, and how to adapt them. This, as I said, I decided to add these slides because we massively use these techniques to do our explainability work. So we know that in the last years, in the last 3-4 years, there has been a massive proliferation of foundation models. I just reported some of them, and of techniques to adapt them to specific tasks. So we are in the era where those models perform extremely good. Okay? The representation is extremely strong, but there is one problem: understanding collapsed. Okay? Because there are models with a huge quantity of parameters. This space contains is like a billion, in the billion, we have billion of parameters, so it is a huge space. Trying to understand what our model is doing and why it is doing some specific, or is doing some specific prediction is really important. But of course, since these models have become larger and bigger, understanding what they're doing on specific cases, it is much more complex. And of course, the explainability research has been a long-standing field in the AI communities, but since most of the application of the AI methods we develop are going to be integrated in end-user applications, we need to address this problem more concretely, because we are in the era of the explainability crisis. Here there are a few examples. I reported some news where some specific AI models made wrong predictions or biased predictions. This is like one Amazon system used in the US to allow, to give access to people to specific buildings, and then they noticed that on one specific category, the performance were extremely low. This is a specific case where there is a bias, and what I will present, what we try to do in our lab is to understand what are these biases and eventually to correct them. And there is another point. I mean, explainability is not only because we are researchers and we want to create problems that do not exist in life, but these problems exist. And we know that there is a regulation in Europe about using AI. We know the AI Act, especially the Act states what? That any affected person subject to an AI-assisted decision should be able to receive meaningful information about the logic and understand the basis of the outcome. So that means, it is very clear, that means that every time you use AI systems to do some tasks, some automated tasks, you need to explain why, especially when these tasks involve people, okay? And we are at this stage, so we have very impressive models. They do a lot of things, but they can, at the moment, there are cases where they misclassify cookies for Chihuahua. In the top one, the cookie was classified as Chihuahua, and in the second one was classified as, no, it was a muffin, okay, sorry. So the point is why the model is doing this specific prediction, which features they are using, and is there any causal correlation between the decision made by the model and the data? These are the questions that we do in our research. So we know that interpretability is extremely complex because we are trying to understanding models that whose representation lie in a huge multidimensional nature. Moreover, in neural networks in general, the feature space comes from an aggregation of multiple of these high-dimensional spaces. So try to disentangle information from this space is extremely complex. But we have to do that because we have to move from what we have today, very big models that are able to provide very accurate predictions, to a model that in the future will tell why you're doing that. So I'm not only interested in saying that the image is a cat with a specific probability, but I'm interested in providing the information that the image is a cat because it has all these features. And this is what we want to tend to in the near future. Here there is a taxonomy that probably you already know. I tried to group together a few explainability methods. So we can see that there are two big families of XAI methods. The post hoc methods, which basically try to explain the decisions made by a model which was already trained. And then there is the other family, which is the intrinsic model, which basically means what? That you create your model in an explainable way since the very beginning. One of the most relevant examples is the concept of bottleneck models, which nowadays try to inject specific concept in the model representation. Okay? Of course, this kind of model can be applied if you have one very new problem, you start from scratch. But when you are in the case of foundation models, and I imagine that no one in this room can create a foundation model because you need a lot of computational power, a lot of data, we have to go to the post hoc methods. So those methods try to explain decision after training. And here there is this distinction between local methods and global methods. Local methods are methods that basically explain individual prediction. So you just provide one image, one specific data, you get the prediction on that data, and then you ask the model why on this specific instance you are making this prediction. The second family is the family of the global methods. So in that case, they try to explain globally how the model works. This is quite important because if you explain how globally a model works, you can add some cue on how the data, on the quality of the data you use for training. And you can indeed uncover some specific biases. So in our recent research, we mostly focus on global methods. You already know these techniques, right? Have you already heard about these techniques? This is one of the most used techniques for doing individual prediction. So the approach is to create some attribution maps by using the gradients of the model. In this case, this is just the output of the GradCam approach. I reported the reference. And the question that this kind of methods answer is, which area of an image does the model pay the most attention to? These are images taken from our recent work in the medical image domain. So the point is, in this case, we are dealing with angiography, and we predict some score for angiography just to understand if a patient has to undergo some surgical intervention. And we say, okay, the score is nice, but the medical doctor needs to know why. In this case, we were able to understand that the prediction was influenced by the presence of the stenosis, the one in the red bounding box. This was some work done at the COVID epoch. Transformers also have another way to understand what they are doing. One method to do that is through the attention rollout. Attention rollout basically takes all the attention scores within the transformer and then does this multiplication over the layers and then multiply these attention scores by the input image in a way to highlight what are the most attended tokens in the image. Okay, this is just a very standard technique. These are all techniques to do individual prediction explanation. Okay, but the point is, okay, if I wanted to understand if my model has a bias, How can I do this by explaining individual prediction? One straightforward strategy might be, okay, I provide multiple images to the visual classifier, I create attribution maps, and then I need to aggregate these attribution maps and do some reasoning over them to get global behavior of the model. This is not always easy because attribution maps have some limitations that come from let's say the features of the gradients within the neural network. So the idea of aggregating and analyzing single attribution maps is not a viable strategy, okay, because they are not interpretable themselves. So the other strategy is to go directly for global understanding of model behavior. And one typical method was using activation maximization. The idea of activation maximization is once your model is trained, you try to optimize the input image that maximize some given output. So in a classifier, you have the last head, which is the classification heads. You just pick one head of the classification head, for instance, the dog class, and then you optimize the input parameters. So at the end, you optimize the image in a way to maximize that specific output, okay? And this is an example. This was done almost 10 years ago. You start at the beginning with a random initialization of the image, then you do this gradient optimization, and you come up with images like this one, even better than this one. These are examples reported in the paper trying to explain some specific classes. It was used for quite a while, but the problem is in this case that even though they optimize and they maximize some specific output, at the end, when you have to understand these things, they are not easily to understand because they generated images which do not exist. So that's one of the limitations. So they are extremely complex to interpret. Following the idea of activation maximization, there were, Nguyen specifically, used some GANs to synthesize images that maximize some specific neurons. Okay? Rather than starting from only random pixels and then trying to optimize the random pixels, they used a GAN. You know a GAN, right? Generative Adversarial Network. So you the idea was start to optimize the latent space of the GAN in a way to generate images that maximize some specific output. And you can see that the quality of generated image was quite way better than the ones we saw in the previous slide. And each generated image should explain some specific decision of the model. And you can see on the rows the different models and the explanation for those models. Of course, one limitation of this approach is that the granularity of the explanations is constrained by the data space of the GANs. Basically, it's constrained by the data distribution used to train the GAN. Okay, if some specific data or some specific data points are not included in the latent space of the GAN, you are not able to explain that specific class. I can do just an example. You want to explain why a classifier is predicting a B, okay? And then, for instance, this is an example we will see later. And then all of the images used for training the classifier contain flowers, okay? So one possible bias is that the model says there is a bee because there is a flower. And let's suppose that you use a GAN and the GAN doesn't have the flower concept because in the training data for the GAN, the flowers did not exist. So in that case, these kind of methods cannot explain that specific bias because the GANs may miss the concepts that in a way can explain some specific decision. Okay, this was the general architecture, and this is something that it is important to, for understanding the rest of the presentation. The idea is that this is the last layer, the classification heads. You pick up one classification head, and then you optimize what? The input space. In the input space, there is a deep generative network, and the input space in again is the latent space, the latent space as input of the model. So you just try to identify the points in this latent space that in a way maximize the output. Okay, so I think I repeated this slide twice. Anyway, the problem here was, okay, these methods were quite good, but of course they didn't gain much momentum because the quality of generative models at the time being was not so high, even though GANs were quite good in generating synthetic images. And also the other point is that given using these images, at the end it is very hard to understand what the model is doing for making prediction. In other words, it is very hard by looking at this image to explain why globally what the model is doing, what the data used for training the model was formed. So, and this leads us to the third part of my presentation. So, from visual to text explanations, because the idea is that those images, okay, were okay. You can just check all these images, try to understand, to get some understanding on what the model is doing. But the most natural way for humans to understand concepts is through text. Okay, and this is the idea that what we want to do. We want to explain, in the past, what we were trying to do is to explain some signals that in the case of classifier were images, but we are not explaining the reasoning. So we don't know the reasoning the model does to make some specific prediction. So the first work we did to perform this global understanding of the models is the approach you see here, which is called the diff explainer. Okay? In diff explainer, we try to follow the activation maximization strategy. And the idea is to optimize text prompts to steer visual generation towards maximizing neurons. So this part is very similar to activation maximization because we follow that specific strategy. What we are trying to do is to optimize the prompts. That's why I presented the different strategies for adapting foundation models, because the strategy is more or less that one. So let's see what we do in practice. So this is our classifier, and the classifier is frozen because we want to understand globally what the classifier is doing. Okay? We start from the output, as in the activation maximization strategy I presented earlier, and we go back. You see here that we have this LDM. You know LDM? What LDM is? Latent diffusion model. Have you heard this word? Have you ever heard? DALL-E, for instance, is a latent diffusion model. It's a generative models to create images conditioned by, for instance, text. So in between we have these latent diffusion models, and then which can be conditioned from by some text. And then what we do, we optimize prompts in input rather than creating the images. So the strategy is a bit different. We leverage these huge foundation models and we steer the presentation, the generation of these foundation models in a way to maximize the output of our model. Okay? So you see just the difference here. This is the difference between the Guyenne approach and our approach. And for instance, it is quite interesting. In the case of B class, for the ResNet 50, the image that maximizes the output for the B class contains only flowers. This can set an alarm. So probably the ResNet 50 was trained with images, with B images where there were mainly flowers. So at the end, the model learned only flowers. This is another case, for instance, of a bias that we found out with diff explainer. The class is flagpole, and at the end, the image that maximizes that class is an image of a flag of the United States flag. This is double bias in this case. But optimizing the prompt on the text space allows us also to do let's say, finer analysis. You see here, for instance, in the previous case, the prompt that we were optimizing was structured in this way. A picture of prompt V, and V was optimized, okay? And we got this kind of images. But we can, let's say, steer the representation in the text space in a more focused way. For instance, in this case, we optimized a texture of V, where V is the prompt we are going to optimize, where the pipeline is optimized. And you can see that in that specific case, for that specific classifier, these are the texture for which the model is more sensitive, okay? Of course, this provides us some additional information about our model. So in the case of B, again, you see that the most important texture, or better, the texture that maximizes the specific class doesn't contain any B structure in any form. In the case of dog sled, there is some snow. In the case of strawberry, there is a texture which resembles strawberries, okay? We can do also for the shape, and we can see that in this case, there is something which is working. In this case, maybe not, because the dog sleds, there is only snow. Even for shape and for texture, there are only snow information. For the B class, we are not even able to create some shape which makes sense. This was a clear indication that in ResNet 50, the B class was completely biased, okay? So the text at the end enables explaining with granularity up to the low-level features in terms of texture and shapes. Here you can see some results that we obtained by using Diff Explainer, because it improved bias discovery at the feature level. This was done for different classes and also for different neural features. So we know that the neural features are the features at the previous layer, at the layer before the classification one, the last layer. So if you move one layer back, you have what are the main concepts that the network is using to make some specific prediction. Here, for instance, for the class Marmot, when we generate the images maximizing these neural features, the top 5 most important neural features, for instance, we see that one feature maybe encodes some texture about the marmot, some other feature, something related to the background, because of course the background is really important. The problem is that if you use only the background to make classification, there is a bias. But to make a classification of a concept, you also need background. And you can see that in this case, we were able to understand different set of features. But the limitation of this method is that the explanations are still in the visual space. So at the end, even though we were able to generate these images by optimizing in the text space, the words we obtained here at the end, when the optimization was done, the words that we obtained replacing the B prompt was without any significant meaning. So we couldn't use those words. What we used was the images, the optimized image to explain some specific concept, okay? So still we are in the visual space. So this led us, what if we really want to understand and explain the global behavior of a visual classifier in the text space? And this led us to let's say, the work after the Diff Explainer, which is Dexter. Dexter was published last year in New Rips. And the key question was, again, is it possible to explain a visual classifier decision-making process within text? So we start from visual classifier. We want to investigate model reasoning for one specific class. And we want to optimize in the text space. And we want to obtain this time some textual explanation for the visual classification behavior. And this is the Dexter optimization process. How Dexter works. This is the whole pipeline of Dexter. You see, that, again, the strategy is always the activation maximization strategy. So the point is we want to generate the text that, in a way, when it is provided to a generative models, generate one image that maximizes one specific class. So you just start from here, for instance, B prediction, and then we move back until we optimize this text. And we still use the soft prompt, the prompt learning strategy, the one I presented at the beginning. So we optimize, we find the best parameters in the soft prompt there that conditions BERT. BERT generate some sentence. This sentence is passed to Stable Diffusion. Stable Diffusion generates one image. This image is passed to the classifier, and then we measure what are the confidence, the prediction confidence for the model. Of course, this is a very long pipeline. There were many challenges that I just reported here. The most important one was the vanishing gradient. So in that case, since there are many different layers and they are extremely deep, when you get some gradient and then you go back, we got, at the end, we were not able to optimize the soft prompts. Another limitation was that we used BERT. You know BERT, right? BERT is this model that is trained in using masked autoencoding, okay? Because the idea was we don't want just to optimize some space. We want some text. We want to create sentences. So to create sentences, we needed a model trained using masked autoencoding, which is BERT, okay? So at the end, you have a sentence, and you want to generate the next word. This was the strategy. Of course, the output of BERT is discrete, so we needed something to make everything differentiable. And the other point is that BERT and latent diffusion model uses different dictionaries. So we had to match these two dictionaries. As you can see here, there are basically two pipelines. There is the text pipeline, which is the one until here, and the image pipeline, which is the bottom pipeline. So this is what there is inside the text pipeline. We used the Gumbel softmax to make the output, the discrete output of BERT differentiable. And then we used some specific mapping matrix between the BERT dictionary and the latent and the stable diffusion dictionary. That means what? The problem is that with BERT, words are encoded with some specific values. In latent diffusion, the same words have different representation. So the idea was try to match this representation. And we had to do this necessarily because otherwise we were not able to create meaningful images in the image pipeline. In the image generation, at the end, once the text pipeline predicts the words, we just simply use the strategy we saw earlier. Okay? Once the soft prompt is optimized, we can get some predictions on the visual classifier, but we can do some reasoning on the images by using the text there. And this allows us to do this textual reasoning, as you see in this slide here. Okay, here you can see some results we found out with Dexter. For instance, we investigated large models, very common models, and you can notice that for the Tiger class, BIT, ResNet 50, and robust ResNet 50 do not contain any bias because the image that maximizes that class contains a tiger. For instead, the Jeep class, you see that BIT and the robust ResNet, they both contain Jeeps, but the ResNet 50 doesn't contain any Jeep. So this is an indication that ResNet 50 struggle with the Jeep classes, and also we did this also for other classes. By using this strategy, we were also able to do slice discovery and the bias. You know what is the slice discovery problem? Slice discovery is to find in the dataset specific slices, sequence of images or images that introduce some bias in the representation. One of the dataset used is the waterbirds dataset, where during training there are a waterbird image only in water scenario, and then in the test set you have waterbird images also on ground. So in that case, you are injecting the bias in the training data. So you want to understand if the model is able to remove that bias and to use the core features for classification. So the slice discovery is a quite common problem in computer vision. The point, again, is to identify some specific slices in the training data. So we want to understand models, but we want to understand not only why a decision is done, but what is the causal, or better, the causal correlation with the training data. So you are doing wrong classification on B because the training data contains only flower images, or because there is a large portion of the data containing only flower images. What interesting things is that, of course, Dexter was almost on par or even better than competitors. But one important thing is that in Dexter we do not use either data or ground truth, while competitors use or data or ground truth or both to do this slice discovery and the biasing. Another example, just to show that Dexter works quite well, we artificially created a dataset for doing edge prediction. Okay, and we did two instances of this dataset. One where 70% of images were of male subjects, and 30% were of female subjects, and the other one completely balanced. When we passed this, we trained the model on this dataset, and we passed the trained model to Dexter. Here you can see the text explanation obtained through Dexter. In one case, it clearly states that there is a bias. You see the slight overrepresentation of male subjects in the caption could suggest a bias in the training data. So it was able to understand and to derive that textual representation by using only the model without accessing anything more. In this case, instead, the model is, Dexter is explaining what the model does, and it states that there is no bias. Of course, this was, let's say, a confirm that Dexter was doing right. Okay, so the pipeline, the timeline of the presentation is that we started from activation maximization. We improved activation maximization with diff explainer by just using the, let's say, prompt tuning strategies. And then we moved to Dexter, where the optimization was done in the text space, and this allowed us to provide text explanations of visual classifier. So, as I said at the beginning, okay, this is quite good. I mean, explaining globally the behavior of a model through text is really much more interpretable than seeing images and trying to understand, to uncover explanation from images. But the point is, what if we don't have access to the model weights? I mean, as I said at the beginning, we are going to use AI models massively also in our mobile phone, but in many applications. And what we do, we are going to use, for instance, API service, including AI. So you don't have access to the model parameters. All the methods we have seen so far, they foresee accessing the weights because they use gradients. So we basically try to optimize the input space or the soft prompt by applying the backpropagation at the end. So for those, you need the access to the weights. So we investigated also this problem. Okay, the case where we do not have access to the model parameters. And this is the one we call the real black box problem, because you have to uncover the behavior of a model, but without but only using the predictions of that model. So this is the problem. Again, investigate visual classifier reasoning without accessing its weight. These are the models we have seen so far: activation maximization, the GAN, and the two models I presented, done by the people in my group. But When you don't have access to to the parameter weights, the real black box case, these methods cannot be used anymore because they are based on backpropagation. This is the one we call dissection strategies. So we want to understand what the model is doing using only a prediction. So the objective is to maximize the activation of a visual classifier for a given class by working only with text. We want to do only text optimization without using backpropagation. How can we do that? The point is, what we can do is, we have our stable diffusion, our generative model, and we know that we can condition the image generation through some sentences, okay? Of course, we want to find the sentence that maximizes the output of the classifier. One idea is just, it is not feasible to test multiple prompts in that case. Of course, we need some signal to steer, or better, to optimize the text prompt to the model. And we want to do this without accessing the model parameters. This is what we do in this new work, which is Unbox. We use some specific technique which was published, I think, 2 or 3 years ago, which is text grad. You know text grad? Have you ever heard about text grad? So rather than using backpropagation, so forget about backpropagation, because in this case cannot be used, what you can do is to optimize in the text space. That means what? That at the end, every step of the optimization doesn't produce new parameters, but produces new text that you can use to, in our case, to explain the model. And this is done by using what? AI agents, so that are specific instances of LLM models, of large language models. So the problem is, again, we want to discover one specific class, which is the tiger class. We start from some input prompt, the PT prompt, random initialization of this prompt. The prompt is passed to our generative models. We generate an image, of course, and we pass this image to the model, okay? The model is completely black. We don't have any access. We have only access to the prediction values, these SST, which are the predictions for the model. Then we start reasoning on these predictions. How? We basically use two terms, two concepts. The one we call semantic guidance and the optimization context. In the semantic guidance, we just do what? We see if the confidence has improved, and we see if it is necessary to do some micro refinement. And yet there are 3 agents. So this agent at the end, the first agent, will see, okay, this is the optimization context, all the prompts that have been used so far. What are the predictions for those concepts? Then we provide also to this agent the semantic guidance values. This basically tells the agent, of course, the objective of this agent is to do what? Given the story, given this value, to suggest some changes to the text prompt, okay? And then this goes to the other agent that, given the prompt, the initial prompt, implement these suggestions to the prompt, and the prompt is provided again back to the input. So you don't have access to any weights. What we are asking is, given the story of the confidence, okay, we start from completely different. In the case of the tiger, we start from random text prompt, an image of a house, okay? Then, of course, when we get the image of a house and we are investigating some specific output, we say, okay, for that specific output, the confidence is really low because that output at the end doesn't encode any house, but only tigers, okay? We say, okay, this is the confidence is really low. If the confidence is really low, the semantic guidance say, okay, probably the image, the text prompt is completely wrong. So the Confidence hasn't improved, so we need to do not micro refinement, but big refinements, because the prompt is completely wrong. And we do this several times until it converges. And we never used parameters. So this again, as I said, this was done using these text grad techniques, where we basically use agents to refine the prompts that at the end generate images that maximize one specific class. What was really nice about Unbox is that we were able to measure the semantic fidelity. That means what? Given one classifier, you have access only to the prediction, the output of these classifiers. Can you understand what each single head implements? Because if you have a model and you query this model online, you don't know what all the heads represent. They will give you one specific class. So the point is, are we able to understand what are the classes that the model is able to classify? Okay? And this is what the semantic fidelity measures. So in this case, what we do, we just measures the prompts we obtained, the text words we learned through the Unbox model, and the classes we have in our dataset. Of course, this is for evaluation. For evaluation, we used the correct classes. And you can see that Unbox was able to identify the classes of a model much better than the competitors. Again, what is really interesting that we don't need to access weights and data, just using generative models. Same time, another question is, are we able to uncover training data descriptors starting from the model without accessing the parameters? This is quite important to understand why we need to understand the text descriptors and then the image that at the end will activate most our model. Because this gives us what? An idea on the training data. I mean, if we were able to understand what are the semantic words that in a way match the one we create, we are uncovering what are the training data used for creating our models. And you can see that again, Unbox is doing quite well, a bit less than Clip Dissect, but there is one point, we never access the weights, while Clip Dissect, which is a competitor, instead uses the weights. Same things is for visual grounding. Are we able to uncover visual information from training images? So the point is, using the Unbox strategy, we want to understand what are the visual features of the training data for that model. Okay? Of course, we don't have access either, again, to the parameters and to the training data. And the Unbox was quite good also to uncover this visual information. By using an extremely black box strategy, with Unbox we were able to identify some emergent spurious feature attribution. For instance, one case is, well, let me see. Yeah, for instance, in the library. For the library case, all the words were classroom, class, cafeteria, textbooks, and during was another text, of course, that there might be some error. These kind of things, of word descriptions, may, let's say, give us an intuition on some spurious correlation in the training data. Okay, let's move to the last part of the talk, is toward causal understanding. So, again, we are doing global explanation. We want to do this in the text space, and we want to do this without accessing the model parameters in an extremely black box way. We want to do a step forward. We want to understand causal correlations between causal correlations. So what we want to do is we want to really understand what the model is doing by using some intervention strategy to identify some specific concepts, and most importantly, to understand the knowledge structure. Okay? The models we have seen so far have a few limitations. One is that, for instance, in the case of Unbox, we had to work with closed set reasoning. That means what? That the possible classes were closed, okay? 10 classes, 20 classes, and we know the set of classes. We don't know the exact matching between the classes and the classification heads, but we knew the classes. I mean, if you want to do explanation in a really black box, you have to assume the open set scenario. You don't know. The model can predict any class in a specific language. So the problem is that the methods we have seen so far assume a fixed vocabulary of classes. Understanding is constrained by the labels of the training dataset. The other limitation is that basically they perform explanation through correlation. So the attribution and maximization identify associations, not causes. And the third limitation is that we lack a structured global understanding of the knowledge of the model. Okay? This is quite important, and we will see why it is important. So, at the moment, what we lack is a framework that is simultaneously open set, causal, and that provide structured knowledge about the specific classifier. So we want to do understanding of a model that, of course, as I write here, requires much more than describing it. So it requires intervening and structuring its reasoning. And this is what we do with Occam. Occam is this open set causal concept and explanation and ontology induction for black box visual models. We call it Occam. You know the Occam razor? Okay? Have you ever heard about the Occam razor? That's why it's called Occam. So the strategy, since we are talking about the razor, at the end is just try to cut concept in the image and see how the confidence of a classifier changes. Okay? Occam works in the open set scenario, so the concepts and the classes are not predefined. They are extracted through a pre-trained multimodal language model. It can be adapted to each image and context. In Occam, we perform causal reasoning through interventions, so the concepts are removed from the image, and then the impact of removing concepts is measured through prediction change. Okay? And this, in a way, identify this decision critical evidence. And then finally, since we do this for many examples, what we can do is we can aggregate these causal effects across images, and we can build a concept level representation that at the end will enable global reasoning. So at the end we create an ontology starting from those images. And this is what basically we do with Occam. So the strategy of Occam is propose, ground in the image, intervene, and aggregate. What we do is, given one specific class, whatever, we ask a foundation model, okay, what are the main concepts describing that class, okay? And we receive these terms here, like in the case of this bird here, we have eye, beak, feathers, macaw, and so on and so forth, okay? Then we use another foundation model, a segmentation foundation model, and we ask to segmentate in the image those concepts, okay? The eye, the beak, and so on and so forth. And the first one is the proposed phase. The second phase, the one of segmentation model, is the ground step. And then we have the intervene step, where we basically remove those concepts. So basically we do some in-painting strategy here, and we remove concepts. Here we remove the eye. You see there is the bird without an eye. Here we remove the beak here. And we send these images to the classifier, okay? Even in this case, we don't have access to the classifier, and then we measure how the confidence of the model changes, okay? And we do this for many concepts and for many images. So at the end, what we obtain is many instances of representation, or instances of concepts within specific classes, And what we do is we aggregate all these instances and we create an ontology based on many, many examples. And finally, what we do is we support the reasoning using this ontology.
Sorry, one question. Do you apply an iteration approach in order to extract concept in different iterations, or do you extract the concept only in a first?
We have both. So we start from these things here, and then we have another strategy I didn't report, that given this image we use attribution maps just to extract some low-level features, but in a second iteration. At the concept level, there are no iterations. So we first do concept removal, and then once we remove the concept, like in this case, we just do what? We do some attribution here, attribution map using again TextGrad because we don't have access to the models, and we hide the most significant part, even when we are dealing with some concept features, some low-level features, sorry. Okay, I was here, so at this point, then we do the ontology reasoning. So at the end, what we do is, for some specific classes, we generate some images, and then for each image, we know what is the drop in confidence when we remove the head, when we change the scale, when we remove the legs, and so on and so forth. So these are specific ontology instances, okay? They're not ontology instances, they're, let's say, we can say some concept level representation per image, okay?
Just a question.
Yeah.
It means that you need to create all the different ontology? Or you have
No, we create different instances, so every time we start from an image, we do the strategy I presented earlier, so, which means I remove concepts, concepts, and then see how the prediction change, okay? For this image, I create one concept level representation, some description, a level description, in this form. For this image, I see that if I remove that, the drop in confidence is 0.4. If I remove legs, is 0.3, okay? For each image. I do for many images, and then using all these instances, I ask a foundation model, a language model, given these instances, create an ontology which basically that at the end may generate these specific instances. So we can support these emergent ontologies. This is, for instance, the ontology we were able to create and that emerged by using the Occam on ImageNet. Okay? So at the end, we created this ontology. So the understanding in this case, since we are grounding the knowledge in an ontology, becomes structured and queryable. Here you can see some results, about concept contribution results and localization. So just to see if the model is able to localize some specific concept in an image. But what it is really more important is this structured reasoning. So what we did is, okay, we used some specific language model, and given the image, we generated different types of description. Standard text description, description structured in JSON, and the ontology I was mentioning earlier. Okay? And then we grounded the language model with these three descriptions, and we asked, okay, multiple foundation models, okay, generate the description for the image by using this ontology. This is what we did in this case, okay? Generate a description of the decision process for a specific class using only the output JSON of the model. And the first case is generate the description of the model using the text strategy, only free text, okay? Is what we did. And then we asked humans to evaluate the description of the problem in the three cases, okay? So just to make it clearer, we started from images, we applied the Occam strategy, okay? With the Occam strategy, at the end, for all the classes, we can create an ontology, okay? This is one output. We did another procedure. Rather than creating the ontology the formal ontology, we say, okay, do structure the knowledge using a JSON without any ontology structure. And this was the second approach. And the first approach is, okay, given the Occam strategy, generate free text that in a way describe the change, the prediction change when we remove concepts. Okay? So we structure the knowledge in three ways: free text, JSON, which is more structured than free text, and ontology. Okay? And then we said a language model, with a sort of RAG we did in this case. Say, okay, provide explanation by using this ontology. This was this column here. Provide explanation using only the JSON, provide explanation using only the free text. And we asked the humans to evaluate the descriptions, the explanations done by the model in the three cases. And you can see, this was done on Amazon Mechanical Turk, that using the ontology led to much more intuitive explanations and better received by humans. Okay? So I think we can go to the conclusions of this talk. So what we are trying to do is, and what we have to do, when I say we have to do, is as a community, we have to move from performance to understanding. We know that we can build powerful models and we can explain their outputs, but we need to understand what these models do, and this requires intervention and requires structure. This is at least what the Occam work tells us. Okay? We need to remove concept and try to understand how the models change their prediction when concepts are removed, and we need to structure the knowledge in a way, and we did this through an ontology. And this means what? That to open the black box, we need to change our explainability paradigm. We need to move from features to concepts. And this is what the community tells us. Also, the concept bottleneck models I was mentioning earlier clearly states, do not work with features, with lower level features, but work with concept. And this is what we did in Occam. We need to move from explainable signals, explainable images, to causes, and we need to change the way we structure our outputs. So we need to give to some specific structure to the knowledge derived from our models. I think I'm done. Thank you.
Comment, question? One, two? Okay.
Okay, first of all, thank you very much for the talk. Really interesting. And I have a question about the last proposal.
The Occam, I mean.
Yeah, about Occam, and especially about the causal part, and how and why do you state causality? Because I feel like what you do here, it's you modify the input in terms of the features, in terms of like an intervention will be, and see what is the effect on the model.
Yeah, this is causality.
Okay,
Isn't
but
it?
what I will say it's these models, especially deep networks, are not linear, are also well known for having weird behaviors. For example, adversarial examples, which could be like looks noise, and the models may think that it looks like this. So how do you interpret this?
Well, I mean, I see your point. I mean, if you do intervention at the feature level, I mean, it is, let's say, a bit far-fetched to say causality. But what we do is we remove concepts. Removing concepts that have some semantics somehow implies some causality, because you can see how the model reacts to removing some high-level concepts. That's why we call it causality. I didn't get the part about the adversarial attack, actually.
Okay, so my question will be you always test for in-domain data for mechanisms that are in-domain. Like you never test whether this causal implication will generalize to an out-of-distribution sample.
Well, in this case, there is no in-domain because we don't know anything about the model. Completely. It is completely a black box. So we don't know anything about how the model was trained.
Okay.
And what we did, of course, when you, for instance, if you select here a classifier, for instance, and then you use generative models, the distribution is completely different. So you are in the case of out of distribution. Since we do this explanation on real samples, but also on synthetic samples, we are in a way dealing with the out of distribution problem.
Okay, and thank you very much for the talk. Really interesting and enriching.
Yeah, thank you very much.
I also thank you for the speech. I was wondering, when we do a strategy like this, so Occam, we are removing the important concepts, but we also remove the background. Now, in real life, we use the background, for example, to classify. For example, the snow leopard is typical from Nepal mountains. So when we saw a leopard and a snow leopard, to classify them, we also use the background information.
I totally agree. I mean,
shouldn't we add a background concept?
There is also background concept added. I mean, I totally agree because when we do as a humans classification, we use an holistic approach. We don't use only like core features of the objects, but we see also the environment where these objects generally. But what we do here is we remove concepts, core concepts, but also let's say background concepts, because it is really important, especially when we are doing fine-grained recognition. As you said, if you distinguish two different leopards, probably use more the background than the core features. So, but this is something that we do. And the results in the paper also include one dataset, one fine-grained recognition dataset. Okay?
Just a small curiosity. In one of the last slides, you put from performance to understanding. Is this one? For me, it's not understanding; it's his interpretation. Just to clarify, because understanding is more the mental process to read.
I agree. That's why I agree. That's why we call understanding. We call understanding because we are moving towards structuring the knowledge. And if you structure the knowledge, you are going towards that process. But I agree, this is a bit stretched as a term. Yeah.
But congratulations, excellent talk.
Can you go again to the Occam slide, please? I'm curious about the concept generation because you use an LLM, right? A foundational model. So to extract the concept.
To extract the concept.
Yes.
Yeah.
I'm not sure, have you tried, for example, more this descriptive concept as, I don't know, instead of legs, short legs or long legs?
Yeah, we're also using objectives.
Yes, because I think that's the point, because the concept phase is a difficult phase to find the concept in the concept bottleneck. So now you are using an LLM, it could be useful.
Yeah, what we do is we extract these concepts here and then we combine with the several objectives.
A predefined adjective.
Yeah, with a list of possible objectives. The main limitation here that you have is in the segmentation model. Okay. Because the segmentation model might not be able to extract some specific, like let's say, very long beak, for instance. The concept of very long in the segmentation foundation model, which is more at the low level, feature, working more on low level features, might be more complex. But what we do is just we combine those concepts.
Okay, because I was thinking more for the causal part that we are discussing a lot about that. Yeah. It would be more interesting to talk about the adjectives of the concept that.
Yeah, I think I'm not sure, but I remember that in the description, so we had also these things. That's why we talk about causality, because we also include not only concepts, but the way these concepts are combined.
Okay, that's all. Thank you for the talk. I think it was so interesting for people not working in visual as me, so thank you.
Okay, I'm happy. Yeah, there is one question there.
Ivan?
Thanks for the talk. It was a really nice talk. I'm not so working on explainability, and this is like my area, like what I want to reach are actually most of your papers. So nice. But my question is more related with the power of your models that you are using to explain. I mean, let's say I have a ResNet 15 or something, or even VIT, and we are using BERT, we are using CLIP, we are using several. Like, they are so big compared to the model that we are about to audit at the end or extract explanations. I see the point that right now what we are doing is auditing and checking the concepts, the ontology, and so on. But in terms of production, like once we discover that our model is the biased and our model take the concepts, is it easy or low? It takes not too much to take or not too much power, like all of those models to extract the explanation from the output of the small model that we want to explain.
I think I missed some part.
Okay,
yeah.
Sorry. What we are doing here at the end is auditing, extracting the concepts, the ontology, and so on.
Okay.
And we are using like CLIP, BERT, all of those stuff.
Models, yeah.
But in terms of after we extract those concepts and so on, is it easy not to use the whole model, the whole BERT, because at the end it feels for me like we are using too much power to explain a small.
Yeah, but the point, now I see your point. But the point is that to do this explanation, you need to have a very large knowledge. That's we use the foundation models. Then you can explain even simpler model like ResNet 50 or ResNet 18. But at least to understand, for instance, if one specific concept is not included in ResNet 50, you need someone that tells you have to investigate that specific concept. So you can see these large foundation models like your knowledge base to start for the explanation. But then in the production stage, you do explanation of only the simple models.
So it's just a follow-up to that question, and it's asking if you are treating these foundation models as your knowledge base, then you always need a model that knows more than yours to be able to explain it.
No, more than?
More than yours. Like, you need these models, like these foundation models, to capture more knowledge than your small, like in this case, your ResNet.
This I totally agree. I mean, if you wanted to explain larger model, you would need even larger model. Yeah.
Okay.
Yeah, I totally agree on this. Yeah.
Yes, that.
Yeah, and another problem, because of course it is not like everything beautiful. There are many issues because we use a lot of foundation models, but foundation models have their own biases. So we have to control the biases of the foundation models when we do explanation of another approach, and it's something that we are working on.
Not for the talk.
Thank you, Concetto. I'm wondering, because we are doing similar thing with extracting the ontology, but for fine-grained distinction of different classes that are very similar. For instance, a flower has 5 petals, and another class, the only difference is the texture, or that it has 7 petals, or things like that. Like, how do we make sure with the human that is not an expert on biology or some very subtle nuances to evaluate that the extracted ontology has also the right edges, the right semantics, like ontology rich level kind of
if the ontology is right.
Yeah, exactly. Like with the human normally doesn't know or is not expert on.
Yeah, I mean, but this is something that we asked ourselves. Of course, we did this for, let's say, general computer vision problem in very simple images, the one you can find in ImageNet. But when you go for domain-specific applications, the only things you can do is to compare, to ground the emergent ontology with some existing ontologies on that field. For instance, this is something that we are working on. There are these, in Sicily there are many types of pear, like the fruit, many types. and the visual changes are very tiny. I mean, it is in the tree, and we have an ontology. I mean, the people working in the field, they created an ontology. So we are collecting now the data. We will. The objective is to make to apply Occam to create the emergent ontology, and then what you have to do is only try to see if the two ontologies in a way match. But in the case of natural images, as we did in Occam, the ontology, the emergent ontology, we were able to extract, merged the WordNet ontology. This is quite interesting because ImageNet is built using WordNet, and by using only the data, we were able to get to that point in a very black box way.
Okay, thank you.
Any other question, comment? Thank you very much.
I'm going to introduce the next speaker, because he's an RDA Lab fellow. It's my great pleasure to introduce our next speaker, Torsten Hoefler. Torsten is a professor of computer science at the ETH Zurich. He's leading the Scalable Parallel Computing Lab, and he's also the chief architect for machine learning at the Swiss National Center for Supercomputing. I hope this works. He's an RDA Lab fellow, so this is why it's extremely exciting to welcome him here to Granada, to our RDA Lab UGR summer school. His research is at the intersection of AI and supercomputing, and Torsten has received a lot of prizes in his field. Most recently, the ACM Supercomputing Prize, the Gordon Bell Prize. I heard that's like the Nobel Prize for supercomputing. The Max Planck Humboldt Medal, also very recently. So it's a great pleasure to have him here. I need to tell you, like from experience in Abu Dhabi, his sessions, his seminars are very, very well attended. Like usually there's standing room only. And the Q&A sessions with Torsten usually last as long as the presentation itself. So please use the opportunity to ask questions, as many questions as you would like. It's a great opportunity to have him here. And please join me in welcoming Torsten to our summer school.
I mean, first of all, I didn't say anything yet, so don't clap. Okay? So because you'll see if you want to clap at the end. Second, as she sets the bar high, I'm Torsten, so ignore what was just said. I'm going to talk about reasoning and sparsity in large language models. So this is actually funny because some people really like small language models, but I'm more like a large language model guy because, as she said, as Amelie said, we are working on very large things. So this talk, it's actually supposed to be a tutorial, not a talk. And I am super happy if you just go, and I'm not even going to slide 2, and you just ask questions. But I will start with the slides. And I will see. If there are any questions, let me know. I can go to a whiteboard setting and I can explain anything you want well, not anything you want. Don't ask me about bees and pollination and stuff like this. But anything that you can see remotely related to the slides, I can probably give you my take on it. But I will start with the slides. And first, I wanted to start with the sparsity in deep learning papers. Actually, one of my highest cited papers that I wrote a while ago. And if you look at this 2021, that's the funny thing. That's like ages ago in machine learning. I mean, if you see a paper from 2021, it's most likely completely outdated, which is partially true, but not for this one, because it's actually not a methods paper. It is an overview paper of what has happened and is very fundamental in nature. So this forms the basis of what I'm going to talk about. If you want to know anything more about anything deeper than what I'm covering here, you can just look at the whole thing. It is the longest paper that was ever published in the Journal of Machine Learning Research, and the editor still hates me for that. But I want to start a little bit earlier, 2021. In machine learning, that is the beginning of time. But actually in humanity, I want to start a little bit earlier. And some of you have seen that motivation before, but I still want to go and motivate you of what's happening right now with humanity, because we are at a new age where we are getting into as humans, which we probably don't know how to control, which we probably don't know what we are going to end up with in 10 years. And this is why you're here, because you want to understand how to use that reliably and in a way that you can control it. So I will give you more technical background of where these things come from. I am not brave enough to talk about reliability of these things, because knowing how they work, I do not understand how the reliability and interpretability of these things functions at all. I can give you my take, but I think it's extremely complicated. But let me start early on. So 2 million years ago, I know, this is going to be a long talk. 2 million years ago, humans discovered materials, right? So it was first stone, then bronze, then iron. And this is actually interesting if you think about it, because before that we were basically like animals. We did not use any tools. We discovered materials to make tools. And many of these ages in humanity were characterized by the fundamental material or fundamental thing that humans used, right? So materials was very early on. And then we know that we went into construction manufacturing. So we used these materials to build bigger things. We built bridges, we built carts, we built, well, cars came later, but things like that, right? And then actually bigger things, big houses and stuff like this. So this is now getting a little bit further. Then came the Renaissance and then the Industrial Revolution. What was the Industrial Revolution? That was the major step in humanity, I would say, that we had so far. In my personal view, the AI revolution is going to be the second major step in humanity. And you and we are alive at the time when it's going to happen. Right? This is something that's very interesting. So the Industrial Revolution was really that we invented things like built from materials that could automate a gigantic part of our work. Because today we can operate cars. Before that, we had to operate everything with muscle power. After the Industrial Revolution, we had steam engines, we had gasoline engines, we had other engines that gave us extremely large power in terms of, physical power. So today, I, as a very frail human, I can operate a 700,000-ton cargo ship alone. Like 700,000 tons. No animal on this planet would even think about moving 400,000 ton objects. We can fly planes, we can drive cars. Okay, cars are not that heavy, I can still push it, but think about it, right? So everything changed. The fundamental thing that changed in the Industrial Revolution is that human physical strength became completely irrelevant. Any frail human can have power over a much stronger human by using machines. Think sadly about warfare, right? So we got to use tanks. So even the strongest human cannot fight a tank. So that is a fundamental change in human history. Okay? So what else happened then? Of course, we didn't stop then because that was all before our time. We were not alive when this stuff was invented. So then we moved into the age of technology, which was the atomic age. That was great, even more powerful materials. The space age, great. The digital revolution, and this is something where I want to stop a little bit because that's where I came online. So about 81 was my when I came out of the womb of my mother. So still with the old way of being created, and that was another interesting way because then we used computers. Like we started computers. Actually, shortly after we realized that we can connect these computers. This was one of the bigger revolutions, not the biggest one, the internet. Like we connected all of these computers together. Now we can communicate over the internet. That's great. And then after a while, we realized that the internet, about 2015, so about now, we have collected so much data in that internet that we can actually use that data without understanding what all of that data does. Right? And that is now leading us to the point. So I want to leave you with that question because we have the physical strength is already irrelevant. Today, intelligence and creativity is still relevant. Think about this. I'm not going to answer that question. But it's going to be very, very, very interesting. Right? And I'm convinced this is going to happen. Now, the interesting thing, I want to now give you a little example of what creativity in some sense means and to rub it a little bit more in because it's extremely hard to define what creativity and human intelligence actually means. Is human intelligence knowing what the capital of France is? Probably not, because any freaking language model can do it, so it cannot be human intelligence. Is human intelligence just emotional intelligence, understanding how other humans behave? Probably not, because unfortunately language models can do that better than humans today as well, than the average human. So now it gets interesting to even define what human intelligence means. But I want to go to an extreme case. I want to go to a game that is possibly the simplest game we have to understand. It's the game of Go. I assume everybody knows the rules of Go. It's very, very simple. You have two colors, white and black, and you're basically, you have to surround the other player's stones with your stones. You have stones, you put them on a 2D grid, and you have to surround the other player's stones, and then you can take them. And then you fight for who has the most stones left when you run out of moves. Right? So it's a very simple game. You can explain this to every 3-year-old, no, maybe 5-year-old, it depends on how far you are, in about 15 minutes, and that kid will be able to play it. But at the execution, this game is one of the most complex games that humans can play. So the rules are absolutely trivial. Place stones on a 2D grid. But the strategy and the tactics in that game are extremely complicated. So there are world championships in Go, which are televised mostly in Asia. So we in Europe, we like football more. So you kick a ball. That's more of an ancient thing. In Asia, they like these kind of intelligence games quite a lot. So they look at it. It's actually, I'm not kidding. These are televised, and millions of people watch these championships. So there was the 18 times champion of Go, and so that is a highly celebrated individual. So Lee Sedol is his name. And Lee Sedol is ingenious. He literally devoted his whole life to playing Go. He started at a very young age. He played Go. He's the most proficient Go player on the planet. And so what happened, unfortunately, he was beaten by a machine, which was very, very unexpected. And I would recommend all of you, there's a documentary on exactly that. It's a very, very well done documentary. How the machine beat Lee Sedol and what happened afterwards. That was live televised, and like all these people who watched were like, oh, that is getting interesting. But I want to tell you how it happened, because it was always considered the hardest game to play. Chess was beaten much earlier. I mean, chess is machinized really easily. Go has a very large option space. But how does it work? So you have a board. Like, as I said, it's a 2D board. You put white and black stones on it. And you play by the rules that I just mentioned. But now we're all kind of computer scientists, so we want to understand how it works. So you model the state of the board as some starting state, in this case S00. So what you do is you ask some kind of function. I mean, you could ask a human, or you could ask some kind of computer, give me a possible move. So where do I place my next stone? Let's call this function pi. After you place that stone, you will get to a new state, right? That you can evaluate again. And now what you do is you ask that function pi multiple times with some kind of random, a little bit of randomness. Many people call this heat in machine learning. So you put some kind of random component in it that you don't get the same move all the time. So you get similar moves. Right? Then you ask this multiple times, and then you get m possible candidate states. So it's like you think when you play. I could do this, I could do this, I could do this, I could do this. Right? You can machinize this. You can ask a machine to propose these steps. And what you do then as a human typically, when you see all your possible options, then you think about which is the best option, obviously, because you can only make one move, right? And what you can do then as a machine, you can ask the machine to judge each of these new states that were just created by a move. How likely is my probability of winning when I'm in that state, right? And now we get probabilities 0.01, 0.00, and so on. So that's now relatively easy. So we have two functions, right? One function proposes moves. One function assesses the probability of winning if I'm at that state. And then what I do, of course, if I'm not totally stupid, I pick the highest probability of winning, because otherwise that would be pretty dumb. And then I do the same thing again, because of course there's another move I have to make. Of course, after my opponent made a move, but we'll do this. And then we assess the probability of winning again. And then we may realize that the previous move was a bad idea, because my probability of winning with that move previous, and then I have a limited choice of option is worse than the first one. This is typically something we humans don't do, because you can't do it in practice, because you can't backtrack. Like once you have made a move in a game, you can say, oh, I was wrong, let me correct this. But of course, in a machine, you can do it, right? You can go forward and backward. That's quite nice. And so then you keep playing this game. And this is exactly what the computer played against Lee Sedol. The computer was simulating all kinds of different options. This is why the computer can track back, because the computer was simulating until the end before the computer made the move. We humans, we don't simulate when we play chess. Okay, the expert players actually do simulate. If I play chess, I don't simulate. I just look at the game. I was like, yeah, it looks good. Let's move this here. I'm not an expert player, as you can tell. But in fact, expert players do simulate, but only 5 to 6 steps ahead, because the option space is too large. A Go player, so Lee Sedol was admitting to actually doing multiple dozens of sampling steps ahead. These computers can do hundreds of steps forward, right? But of course, they sample a very small number of trajectories in the possible space, so it gets interesting. But what was the breakthrough? Because this method is actually known as reinforcement learning. I mean, I'm sure you know all of this. And the Turing Award, the highest prize in computing, like the Nobel Prize in computing, was given to the inventors of reinforcement learning just last year. So I was actually at their award ceremony because I got this other award, which is like the mini Turing Award. So cool, good, that's nice. But what is the breakthrough that happened here? The breakthrough is not reinforcement learning itself, not that strategy. The breakthrough is we use deep neural networks to build the pi function and the v function. That's what Google did back in 2017, so it's nearly 10 years ago. Why am I talking about this now? Oh my God, 10 years ago. It's even older than 2021. So this guy must be crazy telling us all these old things, because that is going to be the foundation for how language models will learn to reason without human involvement. Because right now, what language models do is all based on human data. Like every single thing that these models, not all, but most of it, let's put it this way, because this already started. So most of it is based on language models seeing data on the internet, and most of that textual data on the internet, at least the old one, was generated by humans. Right? At least when we started back in 2016 with training big transformers, that was all human data. Good quality, bad quality, terrible quality, of course. So what this does, this allows machines to generate new data that is reasonable, and now these machines can actually continue from what the humans taught them to learn by themselves with this strategy. And this is called RLVR, reinforcement learning with verifiable rewards. And I will get to this in a couple of minutes, but this is going to be the next big thing, right, after LLMs. Okay, cool. How does this work? Well, actually, what you do in these neural networks, you evaluate this pi and this v function with a simple neural net. At the time, it was a super simple multi-level perceptron. That was nearly trivial. Everybody was surprised how powerful that very small MLP was. I was like, oh my God, this is crazy. And so one of the guys who actually did this, one of the authors is a friend of mine, and he told me he was surprised himself. Right? So that's David Silver is his name. He's at Google. He's one of the co-founders of DeepMind. And I had long dinner with him discussing this, and he was like, yeah, I was also not sure that this would work. So the humans inventing this, they don't know whether this will work or not. Right? This is another interesting insight. When we trained the first version of the GPT models, we did not know whether they would work. Right? But we invested in it and it did work. So what you do is you do the Monte Carlo tree search, and this is a very known technique. And then you go deep on this, and you simulate a whole lot of different options. So take that aside. Now what we have is we have reinforcement learning on these states. Right? Now all of us have used a language model. And now you may wonder, well, how the heck would I use a language model to do this? Because a language model works on text. Like I type in, please help me to find my route to the airport or something like this. How does that translate to this? Well, I want to start with a simpler task that a language model could not do about 5 years ago. The task the language model could not do is sort numbers. It could simply not sort numbers. The reason why it couldn't sort numbers is relatively simple, because the way a language model works, it's simply a completion task. It completes the prefix you give it with the next most likely word. And of course, if you now base it on the internet, it's great, because if you now start a sentence like, the capital of France is, and then you ask for the next likely word, you will totally get Paris, because in the corpus of the internet language that we have created as humans, most of the next words, when we look for the prefix, the capital of France is, will be Paris. Right? This is how the first generation of language models actually work. They literally just give you the most likely completion. In fact, today, and I'll talk about this in a couple of minutes, transformer models like ChatGPT, the underlying technology of ChatGPT and Anthropic's Claude and all of those, they still do that at the core. They still simply produce the next most likely word. There's a lot of tricks at the end, though. So we would go into much more detail to figure out what it really does, but at the high level, it's the next most likely word. So here is a problem, of course. If it says sort the numbers 2 and 3, I think it would be fine, because maybe somewhere on the internet there is the text sort the numbers 2 and 3, and then it says, yeah, the sorted version is 2 and 3, right? But if you have a sufficiently long string of numbers, it's very unlikely that somebody on that internet will have exactly asked or will have exactly have that numbers to be sorted, right? And followed by the sorted sequence. So the first language models completely failed with this, utter failure. And you may have seen this a couple of years ago when everybody was like, oh, my language model can add 2 plus 3, but it cannot add 2,135 plus 5,776.67, because the most likely completion task didn't do that. So now we needed to get reasoning in those models. So how do we do this? Well, you can do the same thing, as I just mentioned. You can take a string, a task, like sort the numbers, and what you do is you ask the language model, how do I do this? How do I sort numbers? And then the language model gives you some answers about a strategy how to sort numbers. And it could say, for example, numbers are blue, which obviously is pretty stupid. But these models are not very smart at the base, so this is actually realistic. But then it could say, look up quicksort. Huh, that may be an interesting one. Or it could say sorting is simple, which is also kind of not helpful. Or it could say split it into 2 sets. And now you could ask the same model, how likely am I going to be to solve the task of sorting the numbers if I assume numbers are blue? Well, that's a very low probability because, I mean, that's the model will know itself that it has said nonsense. But quicksort looks good. Splitting into 2 balanced sets looks good. And then what you do, so quicksort is a sorting algorithm, right? So what you do is you then look up quicksort, right? And then this is how quicksort works. But then you realize, oh, you know, I only have these 7 or 8 numbers. This is probably too complicated, so my chance of winning is higher if I just go splitting it into balanced sets, because that's an much easier task than looking up quicksort and running quicksort. As a human, you would never use quicksort for this, actually, right? Obviously. As a human, you would just look at this and say, oh, yeah, sure, I know the smallest is 2, 3, 4, 5, 6, 7, and then 12, right? So that's obvious. Actually, what I just did was bubble sort. It's even simpler. And then you do this, right? So basically, you play the exact same game as we just talked about, just with text. And the only difference that you have is really the function now. The pi function is an LLM. You have to not ask, the next possible move is actually a string that comes out of your language model. And the value function assessing whether the move was good is another language model. And what you can now do is you can encode arbitrary tasks into this, and you can ask the language model, please go and solve this without any additional ideas, but the language model comes up with the ideas itself by querying the policy function. What is a good idea, how to move this forward? Is this a good state now? And boom, we have invented agentic systems. That is essentially the blueprint for an online agentic system. It wasn't called like this when it was invented, but now agents are everywhere and everybody's like, oh, let's do everything with agents. I think it's a kind of a silly term, but that's a different discussion. The only problem is that with agents, we have way too many of these options and tokens, and so now this is nice, right? Because you can totally decouple yourself as a human and you can simply say, well, solve this problem for me. It's really hard. Prove P equals NP. Or disprove it for me. Go ahead, do it. And absolutely, the language model will attempt this. And if you give it infinite compute, it'll surely solve it, right? Because it could simply explore all possible options, which is, of course, of like nearly infinite size. Of course, it's countable, but it's very, very large. And then if we had infinite compute, we could solve it. And now the only limit we have to run this is compute. Right? That's really the only limit. So, and this is why everybody builds these gigantic data centers. This is why everybody builds these more and more compute-intensive things. This is why the NVIDIA stock value is $5 trillion. Right? Literally that. There's no other reason. And this is why the next big asset is energy. because compute comes from energy, and most people haven't realized this. Yeah, but people begin to realize this. It's all about energy at these days. So, okay, cool. So now, the interesting thing we just learned is basically we have superhuman strategy. We have a computer that is better at playing a strategy game than any human on this planet. Like we just know this. By the way, Lee Sedol, the best human in the championships, after losing that game, he said, I'm done. I will not play Go anymore professionally. He retired from his professional Go. He did not do anything in his career. He's now a professor. So he now teaches other people to reason and think. He's actually a super successful professor. But literally the best human player, he was just, okay, this thing is good. I'll just quit. And what we already know is that the models we use today, ChatGPT and I don't know what, they have superhuman knowledge. They know more about the world than any of us in this room. I would claim they know more about the world than we all combined in this room, right? I mean, you can ask really arbitrary questions about deep biological, I don't know what, and it'll give a reasonable answer. Not always right, but a reasonable answer, right? So factual knowledge is actually quite good. And this was a thing that was, O1 was the thing that was the first model that was invented that combined the two with the technique I just explained. Right? So this technique is extremely foundational, right? And this is why we got the Turing Award for this, we got a Turing Award for this. And so we'll see, maybe the people who combined it will get the next one. Okay, so actually the thing now you may be worried. Now you might be like, ooh, so we have superhuman strategy and superhuman knowledge. If I put those together, I will have superhuman intelligence, because what do we do as humans, right? We have strategic reasoning and we have knowledge, and we combine these two into our actions, into our uttering of words. So that's literally all we do. And well, you could argue that we have some social component as well, so we know love and all of these things, but it's extremely hard to define what that even means. From a technical perspective, we're just reasoning engines and we utter words and we have knowledge. So social aspects and ethics are very hard to define, and so I don't want to get into this. I'm not saying it doesn't exist, I just don't know how to clearly define these things. But now, let's play this game, so we have a couple of minutes time. This is one of the most fun games. Does anybody know this? Anybody know these kinds of games? Okay, what are they called? Exactly, that's the ARC challenge, the Advanced Reasoning Challenge. This is a game that was designed to be a benchmark for machine learning models to see whether these machines can ever outdo humans. And it was designed to be culturally oblivious. So in some sense that any human on this planet, if the human is from Africa, if the human can read or write, if the human is, I don't know, from Antarctica, are there even humans there? I don't know. But if, no matter what, if an alien drops on this planet and can see this thing, should be able to solve this, right? So it's really, really easy, and many of you probably already see the pattern, right? What you have to do. So it's something that I played a lot when I wanted to fall asleep, because it actually keeps your brain engaged, and it's also boring enough that you'll fall asleep after a while. So what you do is you look at these blue and red things, and you figure out what the input to output relationship is. Like literally anybody can play this. You don't need to speak any language, right? You see here, oh, it looks like there are arrows connecting this. Not arrows, but lines connecting this. Okay. You have another example. You have another example. And there's a whole lot of examples, like thousands of those examples to play. AI systems were basically got a 0 score on this until 2023, when these reasoning models was literally at 0. Humans are at 78%, like the average human is reasonably good. Doesn't solve all of those, but is reasonably good. So I'm at 50%, I'm not very good at those. But as I said, I fall asleep with them, so it's a perfect game. Then came these reasoning models that I just talked about. They totally ruled this thing. They went to superhuman performance within 4 months, right? And this surprised famous mathematicians, and everybody was like, oh my God, math is over. Even a funny side story, by the way. Amelie mentioned that I received this prize in computing last year. So I was invited to the Heidelberg meeting, which is the meeting where all of these Turing Award winners and winners of important math and computer science awards meet. Right? So I was there with all these mathematicians, all these Fields medalists, and it was quite interesting. So one of those people gave a talk. And I gave my talk, a similar talk to this one. Everybody was like, yeah, reasoning models, it's okay. But then basically the next guy came and said, we are done as mathematicians. Because you can use that to, he independently, so he wasn't referring to my talk, but he independently explained how you can use a method like this to actually solve all of math. And then the mood in the room was like, there were all these young people. They were looking up to the big award winners, right? Looking for the future, and they were like, ooh, what do? I'm studying math. So that is an interesting one, because you actually most likely can solve much of math with this. But this is the future. But now, can anybody tell me how many boxes will be colored blue in that example? Because here it's 2, here it's 3, there it's 1, right? Give me the number. Actually, I have to look at it myself. I didn't check this for a while. Okay, I think I have a number. Who can give me a number? 7. Anybody else has a different number? Actually, I don't know. Why do you disagree with me? Let me check. 1, 2, 3, 4, 5, 6. I think it's 6 though. Is it 7? Is somebody seeing a 7th? I think it's this guy, this guy, this guy, this guy, this guy. Right? Okay, so the good thing is the best AI system failed with that example. So we still have a role as humans. So we can still at least collectively solve that example relatively quickly in minutes. And by the way, playing these games is going to cost many, many, many dollars in terms of compute time, because it actually, the system wastes more of its cycle. So we are much more efficient also as humans. So keep that in mind. So we are not done yet. Okay, so there are still tasks that we can do as humans that the AI cannot do yet. Okay, but then I wanted to go a little bit more into the recent past. So there was just a press release yesterday. I'm sorry, that was actually the day before yesterday, because I made those slides yesterday. And I didn't think that I would be presenting them today, so 2 days ago. So what happened? OpenAI, a company we all know. I mean, if you don't know OpenAI, it's the company that kind of invented ChatGPT, that's running ChatGPT. No, actually not running it, because running it is in Microsoft, and I'm affiliated with Microsoft, so I'm also affiliated with that stuff. We released, and I'm saying because I was involved in this, we released a big bang press release. A supercomputer networking accelerates large-scale AI training. So what people do these days, we build special systems to run extremely large data centers. So what does extremely large mean? Actually, here in this case, this system is designed to connect 131,000 GPUs. And these are not the little GPUs that you have in your laptop. These are the Tesla-style 10 to 20,000 US dollars per piece GPUs, right? So think about the volume and the cost and the size of these systems. Actually, that's how it looks like. So that is now an AI training data center. And you can, that's a truck, right? That's not a normal car. That's not a car like I got the rental here in Spain. All these cars are very small compared to the US. That's like a US about two times the size car that people drive here. And that's a full-size truck. So you can see these things are gigantic. And then these are rooms full of GPUs. There are 2 of those. They're connected through the middle. The topology and everything is described in this article. And so that is the infrastructure we are building today to train and work with these models. This uses gigawatts of energy, right? So this is a very large energy thing. If you care more about this, you can actually read how the whole system is connected. The network in this paper that was just released yesterday. So here, as I mentioned, I'm one of the authors somewhere here at the Microsoft site. So huge inter-industry collaboration going on. So, and that's what I wanted to give a little bit more of an insight here. What are we doing as humanity? Because most of us don't know what is actually going on building these extremely large systems. So what do we mean? So what I just said, these language models, they run on these gigantic machines. So we built these gigantic machines. These machines, like the one I just showed here, the thing at the bottom, these machines are called supercomputers because they're bigger than, I mean, you know, supermarket, you know, it's like a market, and then a supermarket is a bigger market. And then if you're in France, they have hypermarkets, which is even bigger than a supermarket. I'm not sure, do you have hypermarkets in Spain? Yeah. That exists, yeah, because even in Portugal, okay. Okay, yeah, exactly. So we have no hypercomputers yet, okay? So we are stuck with supercomputers. But this is literally what was happening in the past. So we pledged a whole lot of money into building larger machines to do this. I was involved in the Microsoft thing. So Microsoft back in 2019 put $1 billion into developing new supercomputing machines. So fortunately, I was part of that program, which was great because it enabled me to look at all these things. But what do they do? What do these supercomputers actually do? What they do is they take the text off the internet. We have a lot of text on the internet, right? They run it through a model that many of you know how it works, right? So that's a standard transformer model, and I can explain that in great detail if you want. We can actually spend a whole day just explaining how that thing works internally. But that model is literally a function f of x. So it takes this input as x, it runs a complicated function on. In fact, this function is so large that it requires an extremely large machine to evaluate it. This function is my language model. This function, if you use your language model in your laptop, you may be using Olama or something like this. This is what you download. These weights you download, the 40 gigabyte or something that come flying, is that function. Right? And then this function gives you an output, which is the probability distribution of the next most likely word. Right? So and now you look at this, you read this, and as a human, you're immediately, yeah, of course, it should be harm, and you see the language model is not too bad. In fact, this output vector for any real language model is of size 70,000 more dimensions, because the next possible words are 70,000, including all kinds of Chinese characters and stuff. In Western languages, there are not so many words, but it's also not really words, it's tokens. But let me not get into too much detail. If you want to understand the difference between words and tokens, I can explain. It's really, really easy in case you don't know, right? So in the English language, for example, we have these standard endings, like something is happening, I am going. So it would be totally stupid to store happen and happening and go and going. Why don't I just store happen, go, and ing, right? Then I already have many, this ing is attached to many, many different things, and you see how this works. Right? There's shared subwords in the English language, and it really depends on your language. Some languages have this feature of shared subwords, like in German, for example, with concatenated words. It's interesting. In German, you can make arbitrarily large words by just concatenating words, and so each language is very different. And so what they do, basically, or what we do in this language modeling, is we just look at the most common sub-pattern in the whole text. Is called BPE, byte pair encoding, in case you're an expert, right? And that's what a token is. But typically, it's like a word. Easy, when I say word and token, it's kind of the same thing, but it is typically a word. And now, the interesting thing is, what you know is you have this text, because it's a text from the internet, you know what the right word was, right? And what you do now, during what's called pre-training, you actually update the layers, or you update the weight of those layers to adjust to it. Right? I'm assuming you have kind of basic machine learning knowledge, so that you know what a layer is and a weight. But now the fascinating thing is that the latest model that was, sure, I should update this, because last week DeepSeek V4 came out. So this is a slide from a month ago, I'm sorry. I should have updated this yesterday. But Kimi K2 was the best model a month ago. Last week, again, the Chinese released DeepSeek V4, which is better. That was trained on 15.5 trillion tokens. Think about it. How long would it take you to read 15.5 trillion words? Well, you wouldn't manage, because you would pass away before that, unless you're a very fast reader, but even then it would be unusual. So basically, they train on the whole internet at this point. The number of parameters in this Kimi K2 model is 1 trillion. So it consists of 1 trillion tunable numbers to remember these words. Because as I mentioned, all it does is it represents a probability distribution of the text on the internet. Right? And it has 1 trillion numbers to represent that probability distribution somehow in functional form. We don't know how this really happens, but we know it does it. Right? That's the funny thing. So we are, by the way, what I always like to say, we are right now at the stage where the Romans were when they built bridges. The Romans understood I can build an arch, and when I close the last stone in the middle, the thing does not collapse. Right? The arch holds. Arches are fascinating, because how do you come up as humans with the concept of an arch if you don't know gravity? Right? It's extremely hard. Because you need to come up with this, I put this together, and then I put the last stone, and then it just holds. This enabled building very large bridges. This is what, okay, not the size of today's bridge, like hundreds of meters, but they could build 60-meter bridges with this, which was unthinkable before, because there was no single object, like no tree long enough to actually do it. So they built these arches. And they did not understand gravity. Later we understood gravity. Now I can explain in a physics class exactly why an arch holds. They did not know. We are at the same right now. We know that the thing functions. We have no theory of the information processing inside the thing to understand why it functions. Right? That is fascinating. And I think that we could actually understand this. But I'm not 100% sure. And now the problem is, if you want to go and do interpretable machine learning, you would need to understand how this thing works internally, right? So somehow, because black box methods, I always say, if you use black box methods, you could have used these black box methods with humans for the last 1,000 years, because our brain is also, you could argue, also a statistical language representation machine. Am I just following the most likely probability distribution of language here? Yes, because my sentences make sense to you, I hope. My sentences make sense to you. If I would not be following that probability distribution, I would be talking gibberish, like a bad language model. So keep that in mind. It's an interesting way. Am I a language model? I don't know. But then anyway, it takes an extreme amount of resources to train these models, right? Okay, so now the silly thing is that these resources are getting really expensive. So we are actually today, to achieve more, and this is a unique situation in human history. We are only bound by the amount of energy we can turn into information processing to achieve more human progress. It's not about materials or tools anymore. We are gated by the amount of information processing we can do. Because we understand algorithmically that we can achieve anything with these tools. We're just gated by the amount. So now we need to optimize. We need to optimize two things. We can optimize these language models to be better, which is what many, many people do, like to use less tokens to achieve the same goal, which is a really large field. And as you can see recently with the pricing of those APIs, for example, Claude had kind of an unlimited token budget until people used agentic systems, what I mentioned before, and then boom, you now have to wait every 4 hours to gain more tokens. I don't know, if you're a Vibe programmer, you know this, it's terrible. People stay up overnight because every 4 hours ticks at night as well. So I have many friends who are really hurt by this. Or the second thing you can do is you make the compute system more efficient. So you can use less tokens, or you can make the generation of a single token more efficient using less computing. Right? That's what I want to talk about in the remaining time. I want to talk about how can we achieve that we make each token more efficient. Getting less tokens, by the way, is also a super interesting observation. If you are selling an API, if I'm Anthropic and I sell you Claude as a service, I am not interested in minimizing the number of tokens I'm using to reply to your request, because you are paying me per token. I'm actually interested in giving you longer answers, because then you pay me more. So that is a very interesting observation. When you okay, we can go into details in the break if you want, because there's a huge economic implication here. But what I want to lead us along is really trying to understand how we make things more efficient. And another reason why we want to make this more efficient is that these models are growing like crazy. So this is the good old days, 1960 to about 2015. There was a very low growth in the compute requirement of those models. It was basically following the natural, like my computer gets faster every 18 months, Moore's Law style thing. So nobody was willing to invest more money into computing for machine learning or artificial intelligence. That's the baseline. So here, this is really following the line of my computers get naturally faster. What happened here? Well, there was the invention of modern AI. And then now everybody, and this is a log scale, so this is completely crazy. So everybody is now willing to invest more money. As I said, it's the largest infrastructure built out in human history. So in many places, if you look at the worldwide average, the human investment relative to the GDP of what we actually produce in AI is among the largest. If you just look at the United States in human history, if you just look at the United States, does anybody know what was a larger project in the United States that was relative to the GDP where the investment was larger? There's only one. Anybody can give me a guess? Sorry? So I didn't get it.
The space
No, that was cheap compared to the GDP. NASA was never funded that well. The Manhattan Project is quite up there. Was more expensive than NASA, but not there. No. It's actually, we exceeded the Manhattan Project already today. By the way, the US government, they announced a Manhattan 2 project for AI. Didn't happen as far as I know. It was the build out of the National Railroad system. That was more expensive. Like the universities like Stanford we know today, they were conglomerates building railroads. That was extremely expensive. But however, in next year, if the growth continues like this, next year the infrastructure growth for AI will outdo the railroad system. So then it's definitely number one. Another interesting fact is that just Microsoft alone invested $32 billion into AI infrastructure or cloud infrastructure just the last 3 months, just the last quarter. $32 billion. That is more than the GDP of many countries in that area. So I should have checked what Spain is. I would guess it is there, right? So it's an interesting question because it's only 3 months. Okay, so now I want to go a little bit more into detail on the technical side. So this was still on the motivation. By the way, if you have any questions, as I said, I can diverge arbitrarily from the slides. It has a down and an upside for you guys because I will then not have a good red line if you diverge me. I'm happy to do this. But the upside, maybe it may be more interesting for you. So if you find the slides interesting, we can go with that. If you have any other questions about LLMs or reasoning or stuff like this, I can go into tangents. So please don't hold back. But for the remainder of this talk, I want to give you definitions, which I find quite important because we need to speak the same language. So one definition is when I talk about performance, I mean compute performance. Because many machine learning people, they often use accuracy. They often use performance for how well a model actually does solve tasks. In my terminology, performance is compute performance. When I want to talk about how good a model is, I talk about accuracy. Okay? So these are two different terms, and this is very often confused. When I talk about quality of a model, I also mean accuracy, essentially. Right? These are both data science terms. Performance is a compute-centric term. When I talk about pruning, which many people may know, I mean that you can remove weights in a network to shrink them to a smaller size. This is a subset of sparsification. So sparsification is a more powerful concept that many of you are familiar with. I just want to make sure that we are not getting confused here, because now it's going to be a little bit more technical. Okay, cool. So yeah, in case you care about these numbers, you can find them. And I hope the slides will go online somewhere later that you can find these things in case you want. So now the first thing I want to get clear is that many people just think, oh, the last 40 years were wonderful because there was this thing called Moore's Law, where, who knows Moore's Law? Okay, so it's about 10%, I would say. So Moore's Law says that every 18 months, the number of transistors in my chip doubles for free. That's what the original Moore's Law said. So literally, if I just wait 18 months, I will get a chip that has twice as many transistors for the same price as I got the one before, at the same energy consumption. That has happened for 40 years. Not kidding. For 40 years, we were writing Moore's Law. So basically, every 18 months, Intel cranked the crank, and we got a better chip, twice as fast. And then, of course, companies like Microsoft immediately consumed that speed to give you more complex operating systems like Windows. And so this is what happened. So you can see this here from 1975 until 2015, approximately. As I said, 40 years. It's more like 1973 or 1960 something to 2007, because 2007 something changed. Moore's Law slowed down. What was the reason why Moore's Law worked so well? I mean, first of all, one thing changed here in 2007. Another law that most people don't know, it's called Dennard scaling. Who knows about Dennard scaling? Most people don't. Okay, you learned something new in this talk. So Dennard scaling is that gentleman. So by the way, Gordon Moore was one of the founders of the company Intel. I mean, many of you know the company Intel makes these CPUs, right? The blue logo with like, okay. Dennard was at IBM, another company that made computers. And Dennard basically said, it's another law. Whenever I shrink the size of my transistor by half, the energy consumption of the transistor goes down to half, which is extremely important because the only reason why Moore's Law happens is we made these transistors smaller and smaller and smaller and smaller over time. So the energy consumption followed of these transistors. So what did that mean? If the energy consumption follows, then my energy budget per chip is about the same. Right? When I shrink them by half, energy goes to half. I get twice as many, so it's great. I still have the same chip size. Why is that relevant? Yeah, because the problem is that I need to cool these chips. Do I have this here? Yes, the typical watts. A chip is like this size, computer chip. how many watts can I take from a piece of silicon of that size before it melts? You see that? It's about 200. Because here it stops scaling up. So early chips used very little energy, but then they stop at about here because there's no way to get more than 200 watts out of an area like this before the thing melts, because the energy density at this point today is the same as in a rocket nozzle. You know, the thing that drives a rocket. It's the same heat per square millimeter. And there's no way that I can get more out of this before my chip melts. I mean, there's liquid cooling and all of that, but that gets you another 50% or so on top of this. So now, unfortunately, what happened in 2007-ish is the Dennard scaling stopped. Moore's law continued, actually. I mean, the transistors got smaller and smaller, but due to quantum mechanical effects, they got so small because what they need to do is they need to insulate. Right? Remember, what a transistor does, it turns off and on. So it needs to insulate electrical current. And if your layer that insulates you from your neighbor gets smaller and smaller and smaller, and at some point only 10 atoms wide, you have quantum effects that these silly electrons, they just tunnel through because the barrier is not big enough anymore. And that's what happened here. So we get the things so small, like single nanometers today, that they don't hold anymore. So the Dennard scaling stopped, that's a problem. So Moore's law is dead. And what happened really, we went from a very large, these are transistor pictures, to smaller and smaller and smaller and smaller transistors. So today we're at 5 and 3 nanometers, but that's kind of fake. And then we couldn't hold it anymore. Right? So we they don't hold the charge anymore. They do, more or less, but it comes at a larger energy loss cost. Okay, cool. So that's part of the problem. And we can go into much more detail, but for this audience, I would say that that's enough to understand that in at least the way we built computer chips the last 40 years, there is no way forward to make them faster. Like we are stuck. And that's unfortunate. It has been lasting for 40 years, and now it's over. The only way to get faster chips today is to go to completely different technologies. Either we could talk quantum computing, I could tell you all about that, but we don't have enough time. We could talk about neuromorphic computing, we could talk about analog computing. None of those is at a level today where we could actually use them for anything useful. Like we are still using the standard chips in your phones, in the data centers, and that's a problem. Now the only way to get more compute, as I just mentioned, humanity's progress is limited by more compute, right? We need more compute, but the only way to get more compute is build bigger data centers and invest more energy into them. That's a very sad statement, right? So maybe we really hit a limit. We don't know. And this is why, again, I want to motivate you to listen to me more about talking how to make these models more efficient, because we cannot just wait 18 months and they will be faster like we did the last 40 years. Actually, it was a very nice time. Optimization didn't play a role because we were just like, okay, yeah, we'll wait and it's going faster. So now one way is to use smaller models. As I mentioned, these models have trillions of parameters. Why wouldn't I just use millions of parameters? Well, the unfortunate thing, what I had to skip in this talk for time reasons, is that the only reason why language models are so powerful is because we scaled them up in the first place. Right? We started with small models, and now we went to trillion parameter models because you need a certain capacity in the model to learn the probability distribution of text on the internet. That's essentially what it learns, as I mentioned. And now the option space for next words given prefixes is very, very large. And it's even funnier, it is a very fuzzy problem. Because if I want to complete the following sentence, Torsten is, you could complete it in many different ways. Right? The next token, actually there are many probable tokens like stupid, entertaining, dumb, or whatever. You can make up the any next. That's all plausible. They're all plausible words. Right? So smaller models will not be able to represent this option space that is fuzzy and extremely large. Right? So these models that seem extremely intelligent today to us, they're nothing but statistical text completion engines in an extremely large space, like trillions of parameters. This is what's really happening behind the scenes. So downsizing may be possible, but is actually one of the harder ones. So. And there is a microchip. And so we can have operator factorization. That's a little bit more of a technical detail. The funny thing is what these models do is actually they work on linear algebra spaces. They work on Hilbert spaces, actually. So there are matrix multiplications. You take a vector. Your word is represented by a vector. Again, if you care about this, I can totally explain that in detail, but let me stay at a high level. So each token or each word is a vector. And what they do is they project this vector into different spaces. And this is how they work. So now each matrix vector multiplication, which is what's happening in those models together with some nonlinearities, each matrix vector multiplication implements the transformation, or what many people call reasoning, within that model. Okay? Now, how does that work? Now, what we could do is we could now see the matrix itself as an operator. Because what does a matrix do? It's a basis transformation. Right? You take an input vector, you multiply it by it, and after that, the vector is represented in a new basis. Like if you know linear algebra, you probably learned this in your A levels, right? So great. Does anybody can do this? Great. The only thing is these matrices are very large. They're like 12,000 dimensional, and then it gets extremely hard to reason about what's actually happening. We could factor these matrices into two smaller matrices to represent the principal component, for example, of this basis transformation, such that I'm maintaining the gist of what's happening in this transformation. Right? Many of these matrices actually can be compressed quite well. Operator factorization is one way to compress it. So you take a single matrix that is n times m, you decompose it into two matrices, A and B, and each of those is n times r and r times m. This is lossless. If the rank of the original matrix is r, then you will not lose anything. Unfortunately, for real training matrices, the rank is usually full rank, so which means the rank is either n or m, whatever is smaller in this matrix. So this is an interesting scheme. I will not talk about this. This is a mathematical trick. If you're a mathematician, you will totally love this. You will do this, you will realize in practice it doesn't work that well. So in theory, this is great. One thing that is super successful, what most people do today, is called value quantization. So you take, and this is now a very foundational principle. When we compute these models, I did not tell you how we compute them yet. I told you there are 1 trillion parameters in these models, right? So there are 1 trillion numbers. A parameter is a number. But how do we represent these numbers? Because in a computer, we need to represent these numbers somehow as ones or zeros, right? We all know this. They're so-called binary representations. So most people, when we started training, used 32 bits per number. So a so-called floating point 32 value. Right? So this is a mantissa and an exponent, and I hope most of you know how that works. So we have a number that's represented by 32 bits. But now you may wonder, well, actually, is 32 bits enough? Well, yeah, it worked, so it's enough. But is 32 bits with 16 bits be sufficient? Or could we do it with 8? Could we do it with 1 bit? One question to you is, and do we have any biological person? Our brain is also a binary computer. Right? So we have these neurons and these synapses, and we understand pretty well how they work today, and they fire. Right? Firing basically means I'm sending a 1 along a line, and not firing means I'm sending a 0. I mean, I'm not sending anything. Right? So we are an asynchronous system in our head. So now, so I'm putting a 1 on a line, and then there is a receptive thing in our brain that receives inputs, right? Because it's a network, it's a neural network, essentially, right? So the input comes now from multiple different signals. How many bits does the human brain actually compute with? Does anybody know? Does anybody have a guess? So what you have, and let me just finish the explanation that everybody can follow. What you have is you differentiate, well, it's an analog system, right? When a neuron fires, it puts a certain voltage on a line, and when another neuron fires, it puts another voltage on a line. These voltages are added up when they get to the receptor, and so how many different voltages can the receptor distinguish? You can measure this. You can cut a brain open and attach probes, so I don't know how they actually measure it. But you can somehow measure how many voltages you can distinguish. Yeah, so what's your guess?
But my guess is that it's variable and it will depend. I will guess it will be something like the brain. I expect it to be something like an optimal length or optimal coding for like encoded with little bits and really complex signals for way more big. So be adaptive, which is something that neural networks are not right now.
But there is still a range, right? So we're probably not at 100 bits. So what would the range be? I agree, there is a huge variability, but if you measure the average, any guess? Yes?
Could it be floating to 120 bits?
120 bits, no, that is...
120, 40, depends on
40, no, that's too much. That's too much. Yes, it's way too much. Our devices are not that good. I mean, mine is not that good. Yours is better, I'm sure. Anybody else? Yes?
Around 20.
Around 20 is still too much. I'll give you. So they measured that we can distinguish 24 voltage levels on average. So the log of 24 is 4.6. So I am a 4.6-bit computer, essentially. You're probably at 5 bits, or not. But none of us is significantly more than that. So why do we compute? Why do we represent the values in deep neural networks with 32 bits? Well, we don't know. So what a huge gain is today is we shrink for each of those numbers that we represent, we shrink the number of bits. Today, it's standard to compute, to train models at 16 bits. Everybody trains at 16 bits. Nobody trains at 32 bits anymore. Some values are 32 bits, but not all. If you download an Ollama model to your laptop, you're most likely using an 8-bit version. If you're doing the highest compression, you will be using a 4-bit version. Now it gets interesting, right? So we say humans 4.6 bits, so we're already below that. Actually, the most modern quantization algorithms, which we release with partners, they go down to 2 bits or even 1 bit per weight, but they're very advanced, so they do very strange stuff. So this is extremely valuable, this quantization, but I'm not teaching you all the details here because this is done. I mean, we understand how to do it. So it's pretty clear that you cannot go much below 1 bit per weight because, I mean, what is it if it's not on or off? The way you can go beyond 1 or below 1 bit is you just consider multiple bits in the same space. Right? So then you can go below 1, but it's minor. So we're at 4 bits, and 4 bits is kind of the minimum reasonably we can achieve. I can even prove this that information theoretically there is something to 4 bits, but again probably too much for here. But it's super important. Like anybody does quantization. Like you train your models in higher precision, and then you quantize them down to super small, like usually 4 bits or 8 bits. Another thing you can do is you can just apply standard bzip or zip methods. You can just compress it with your I don't know what you like, zip or something. That is usually terrible. That does not work. But you could. One other thing is parameter sharing. You could now think about, could you use the same parameter for multiple places? Yes, there's a question. Yeah, excellent.
So with the optimization of the models, how are we benchmarking the trade-off between the efficiency and the accuracy?
Exactly. That's a very good question. So the question is, I can repeat it. The question is, when we let me rephrase it. When we compress these models, when we do any of these things, we're going to lose accuracy of the model. Because obviously, if you compress too much, the model gets too dumb, right? And now there is a trade-off, right? Because otherwise you would just go to 0 bits and be happy. So obviously, as you compress, the quality goes down. Absolutely. The question is, how do we assess this quality? There are many metrics. So for example, this one standard metric in training is called perplexity. So perplexity is a metric where, remember, you do the next word prediction, right? And now there is, you can of course measure what your hit rate of the next word prediction is with respect to your actual training corpus. Because you can look at the statistics of the training corpus. If I say the capital of France is, and the model says washing machine, not good. If you say Paris, oh yeah, check. So you can now measure how often it hits that, right? And this is a very simple statistical technique. That is not very indicative of the smartness of models, which is very funny. A model can be a perfect next word predictor, but not be very smart. So to get to the smartness, there are these real-world benchmarks like MMLU, HelloSwag, there are GSM8K. There are many benchmarks that are typically multiple-choice questions, which humans have designed. So for example, Mary has an apple, Peter has a pear. How many fruits do Mary and Peter have together? Option A, 15. Option 2, 2. Option 3, 1. Option 4, 96. And then the model gives you 1, 2, or 3 as an answer. That's MMLU, essentially. There are 100 or 200,000 of those questions, and if the model answers them right, what's the percentage of the model being right? Does that make sense? And then you compress your model, you benchmark it on these question sets. If it's still good, you're happy. You compress it more. The moment it degrades, you're unhappy. What we do in production and in practice is we typically say 1% loss is okay. If we exceed 1% loss, then we are unhappy. So what we can do is we can compare to a full precision model going to 4-bit. We can lose less than 1% on MMLU on these question-answer data sets and still go to this bit width, which seems reasonable, right? I mean, 1%, I'm sure. It's in the noise anyway. Does that make sense?
It makes sense.
Yeah, so it's a very clear benchmark.
I have another question, if I may.
Of course.
It's more of futuristic maybe and towards the governance. Are we going, like with the accuracy or the trade-off, are we going to reach to a level where we are going to have a monetary metric on that, let's say per accuracy of per a barrel of oil or a joule or a dollar value?
Yes, we indeed have that today. I mean, the way, for example, internally at Microsoft, how we measure these things is the cost per token generated. So you can measure, if you know the cost of your machine, right? You know how much you paid for it, you know how much you paid for it initially, you write it off after 5 years or something like this, or maybe 10 years, I don't know, that's a business decision how long you run these things. You know how much energy it takes to produce a token, you know how much energy costs. So now each token, you have so many tokens per second, and from that number you can now compute how much it costs you per token. That's usually in the like fraction of cents, of course, it's a very small amount of money per token. And then you can compute exactly what the economic impact is of generating these tokens. That is the main optimization. All of that is basically expressed in this. It's just that it's extremely complicated to get to these real dollar or euro values, depending on where you live, or AED, Riyadh, what do you have in the UAE? Exactly, thank you. So it's very hard because the price varies greatly depending on who you are. NVIDIA will give you a very different price, for example. Does that make sense?
Yes, it does.
Yeah, so you can compute it for every real system, and people do this very much in practice.
Thank you, sir.
So now the last thing, any more questions?
No.
I love this. I mean, if you have, yes?
About computation and number parameters.
Yeah.
If you want to buy to 8-bit, for example, there is any relation between 2 parameters at 8-bit and 1 parameter and 16 bits?
Oh, I see. So you would say that you wanted to quantize them, each parameter in a different bit width, potentially, to achieve better accuracy.
Yeah.
Absolutely. So people have been trying this, but it's now you have a problem. So we know how, so it's not practical, people don't do this in practice, but I'll explain you exactly why. So remember, you have 1 trillion parameters. Right? It's a large number. So and now you need to remember, if you now have some parameters in 16-bit and some parameters in 4-bit, you need to remember which parameters is in 16-bit and which parameters in 4-bit, right? If you have this in 1 trillion out of 1 trillion parameters, how many bits do you need to remember the offsets of these parameters? Oh, it's a disaster, because 16 bits or 4 bits is only 16 different values you can differentiate. So just the meta information for remembering what is more expensive. So now you could now say, okay, I can encode it in every value, right? I could just mark the value itself, whether it's 4-bit or 16 bits. That requires 1 bit. As soon as I allow you 4-bit, 8-bit, 16, 32 bits, it needs 2 bits. And then you already have half of your budget for just remembering what is going on. Yeah. And now you see where this is going, right? Yeah, yeah. The 4 bits are so small, you have basically no freedom remembering any other information because you'll need at least 1 additional bit, which is already 25% of your budget. Oh, that's terrible. So what people did, what we actually invented at Microsoft a long time ago, is another cool method. It's going a little bit into detail, but you seem to like that detail. So what we do is we say, well, you know, we take 16 or 32 of those numbers together, and we mark them as 4-bit or 8-bit. And now we have a nice block of those. So the relative overhead goes down because we already have 32 or 16 of those. And then we put them together with a scaling factor. This is today supported in hardware. So what's called NVFP4, NVIDIA's FP4 version, is indeed 16 FP4 numbers together in one block. You cannot use them separately. Like they're different values, but they're processed as one block, together with an 8-bit scaling factor. MXFP4 is basically the same thing, just of a block size of 32, so slightly more efficient. Does that make sense? It's really about representing these numbers. Your idea is great if you have large number of bits, but for such small, it's getting very hard.
Okay, thanks.
Yeah, sure. Any other questions before I go on? Yeah, please.
If you go to slide 4.
If I go to slide 4, you say?
Yeah.
Oh gosh. Let's see. Yeah, they have a whole lot of animations here. That's the. Oh, no, I think I can just press. I can just press 4. No, I can't just press 4. That's the problem. Can I just press 4 here? No, I can't. Okay, well, I'm not good at PowerPoint. This one. Yes.
So we say value function is another LLM trained on known examples.
Yes.
So does this means that we are going in a direction where the supercomputer can think like the whole humanity already did, and maybe can get some correlations that usually a human cannot do, but maybe it cannot do something that is completely uncorrelated?
Yes and no. So exactly. The thing is exactly, because you have this gigantic knowledge base, so the computer can now correlate things that a human mind, a single human mind cannot perceive. I mean, we somehow have these great insights where much of it is randomness. So some human mind comes up with a great idea how to correlate two things and then gets famous with it. It doesn't mean that the person was the smartest one, just had a good idea, right? And computers can now automate that. Exactly, that's your first question. And yes, the answer is yes. But now your second question was, can we actually create truly new things that is not in the training data set? And the answer is yes. And you know what? You know why? It's called hallucination in language models. Everybody thinks hallucination is a bad thing. I think constructive hallucination can be a good thing. So what most people say is hallucination is something when I say, oh, the capital of France, I like this example as you can tell. Capital of France is Madrid. And then we say, oh, the language model hallucinated, it's bad because we know it's wrong and blah, blah, blah. We want to avoid hallucination. Absolutely. Even though there will be at least one human on this planet who I will ask this question and the human will say Madrid. Pretty sure. So humans do that as well. So, but now, if I am a scientist, how do I come up with new ideas? I inspire my brain to go beyond my current knowledge, because otherwise it's not a new idea, right? So we need to come up with new ideas. So I could make it, what I usually call is make an educated guess. I come up with a hypothesis. Hey, usually it's going like, let's try that. That sounds like a good idea. Nobody has tried that before, so it may be new knowledge if it's successful. A language model can hallucinate a new idea like this as well, right? Not in the stupid example like with the city where we know the fact. I'm sometimes wrong with facts as well. I hallucinate as well. But I use constructive hallucination to create new ideas. And then the only difference I do today to a language model is I just don't state it as if I'm absolutely sure about it. That's a huge problem with language models. They always state things and they're 100% sure about this until you tell them, oh, I think you're wrong. And then they're like, oh, sorry, yes, I know, yeah, 4 plus 4 is not 16, I know. And then they pedal back, but they state it with absolute certainty in the first case, right? And it's even funnier because they're so abiding to you. If you tell them that a correct fact is wrong, they will still, oh yeah, it's also wrong. It's another problem. But anyway, I'm diverging here.
But still, the hallucination would be something that is somehow in the past archive. So some correlation there and there.
Not really, because like, how do humans hallucinate most if you're drunk? Right? That's just a fact. No, I'm not kidding, actually. If you want to stimulate your brain to create additional knowledge that doesn't really exist, you get into a state of either drunkenness or extreme tired, being extremely tired. Then you will create random things. Your brain goes into a more random mode, which many people do for fun. I'm very creative when I'm extremely tired. I'm not talking about being drunk. I'm never drunk, of course. And so in that mode of operation, you can actually come up with new ideas. Many people say I have a good idea in the shower. Most people don't have good ideas when they focus on things. Most people have good ideas adjacent when you're not focusing. Hallucination. Because this is exactly when it happens. Oh, I'm not really sure about this. I have some random, oh, that's a good idea. Language models work exactly the same way. It's called temperature. You adjust the temperature. If you want the model to be more creative and hallucinate more, you just say, temperature is super trivial, by the way. We've seen this output distribution of possible next tokens, right? When you dial up the temperature, you basically say, well, let's not take the single token with the highest probability. Let's actually consider the top 5 tokens and make a random selection out of those. And if you now make this large enough, it'll be totally random. You'll be just picking random, then you don't need a language model. But if you make the temperature reasonable, it'll be like, oh, let's choose this next token, which is kind of like unlikely, but you know, I'm like drunk, I can go ahead and do, no, I'm sorry, I'm tired, I can go ahead and do these things. Does that make sense? So you can totally dial the model. So if I put a model in research mode, I dial up the temperature. Of course, I get more random trajectories, which go into idiotic things, but I may have the one trajectory that is really a winner. That's again where I need a lot of compute. Because what I do in RLVR, which is this reinforcement learning with verifiable rewards, is nothing but taking the model, dialing up the temperature a little bit, and then it generates 1,000 possible reasoning paths, which is extremely expensive. But you just let the thing run. And what you need is a verifiable reward. You need to make sure that you can test at the end whether the result is correct, because otherwise you don't know if it's nonsense, right? But now, there's a nice thing in math. This is why math is pretty much solved. Many math things, I can prove whether I found the correct result. Let me give you an example. If I give you the task to factor two large numbers, we don't have a good algorithm for it. And I'm now telling you, I want you to factor the number 475,776. You will have trouble doing this. I'm sorry, you may. I will have trouble doing this right now. I would probably ask a machine to do it for me, right? The machine would also not be able to do it well because it's a hard problem to factor large numbers, right? Actually, 76 is easy because it's divisible by 2, so that's a stupid example. Pick something that looks like prime. So factoring is a hard problem, but it's super easy once I give you two numbers that are, and I claim it's two factors of this number, I claim this is true. You can easily check it by multiplying the two numbers. There are many, many mathematical problems that have this property that they're easily checkable, like factorization, but really hard to solve. Many NP-complete problems have this property. In fact, NP-completeness, the definition of NP-completeness bases on the checkability in polynomial time, right? Because otherwise it's not NP-complete. So most of our math problems, in fact, are verifiable. So now what we can do is we can just let the language model explore proofs, and then we can prove that the proof is correct relatively easily. And that's what RLVR is. That's what many of these people did, is they solve very hard math problems. They define problems that are hard to solve, but easy to prove correct. They run with the hallucination mode on, essentially. Thousands of reasoning trajectories, let the model go ahead, and if it ends up with the right solution, we say that was a good reasoning path. If it ends up with the wrong solution, we forget that reasoning path. Right? You throw a gigantic compute at this, but what you then get is a new set of trajectories. And this is what we do in RLVR. Again, I keep using that term. It's a new big thing, right? This is what we do there. We train the language model then on those trajectories to use those for the next best prediction. Now you have a self-improving language model. Now you have a language model that solves problems. It's like a human. Like if I'm solving problems, I'm remembering how I solved it if I'm successful. If you now train the model on these successful reasoning trajectories that it randomly generated, the next one will be more successful for a similar problem, right? And now you run this in a loop. And this is what these gigantic computers do. They run this in a loop right now. There are thousands of computers running millions of these reasoning trajectories while we are speaking here, improving themselves to be better reasoners. This is where all this compute goes. Does that make sense? It's actually really cool if you think about it. And the human is out of the loop. The human simply defines, oh, that's the problem. The computer can do the rest. And this is what's fascinating. Because actually, I claim the computer today can already create the problem as well. Like, you don't need the human in the loop. You just need the human to turn it on, and it'll go away, supply the energy. So that's a little bit scary as well, if you think about it. But it is what it is. Make sense? Okay, cool. Any other questions? It's a fascinating field, yes.
So my question is about good hallucination models.
Yeah.
Can we reach like a model that hallucinates in a good way? In the sense, I can go very creative with it.
Sorry, like your audio is too silent. I don't get a speaker here, I think.
So I can go very creative while discussing with an hallucination model. Because as far as I know now, all like big companies are trying to have models that do not hallucinate.
Yeah.
If I want to reach a model that hallucinates, how I'm gonna have this?
and now we have to get into the definition of what hallucination actually means. So most people use hallucination use the term hallucination when the companies say, I don't want a model that hallucinates, that it makes up things that it should know, right? And again, hallucination is a natural process. Hallucination is a general process, in my view, where we make up things, right? So for example, when I say 4 plus 4 is 18, I'm making up the 18, but I should know that it's actually 8. So that's what most models call as a hallucination. But what I'm asking, if you ask me the question, what is nitrogenase or something like this, then I would personally not know. I should know maybe because it's a well-known term, but I don't. And then my hallucination may be valid. Like in science, as I said, science is fundamentally a process of hallucination because you need to create new facts that you then prove correct, right? And so now there are these two different kinds of hallucination. The one that most people call hallucination, where I should know better, right? That is the bad one, right? And that's clear. But then there is this case where I don't know, and I should then prove that it's correct. That's what I call constructive hallucination, right? So you don't want to destroy constructive hallucination, but you want to destroy the hallucination that most people call hallucination, right? And now the way to do this is you can ground a model in data. This is what most people do today. You can have the model query databases where this information is just in. So for example, if I wanted to ask what my salary is, it's on the internet, unfortunately. So you could go and now Google and find it in some Swiss public database, right? And so, but of course you could also guess it, right? If you guess it, you may be constructively hallucinating, but if you would be really thorough, you would look it up in the database. So that's how these models behave as well. They can give you a guess, or you can ground them. It's called grounding. You can ground them in real data where they go ahead and actually look it up. And today, when you talk to your favorite language model, it's a mix of the two, because grounding is very expensive, right? If I now make Gemini go and look through all the internet trying to find this is going to consume at least 10,000 tokens. It's not so easy to find, right? Or if I make it guess what does a professor earn in Switzerland, well, I mean, it can give you a reasonable guess, right? Does that make sense? I mean, the grounding is expensive but possible. If you do health, so I'm working a lot in medical applications, for example, you always want to be grounded, right? Because you don't want to guess and have people dead after a while. So it really depends on the importance and how much you want to invest.
But then can we fine-tune a model to push it for good hallucinations?
Yes. This is exactly what I meant with the temperature.
Okay.
So
I mean, my question was this, basically.
Yes. But I see. No. Okay. That's the problem, exactly. When you make the model more creative, yes, it'll give you about as much total nonsense that it gives you reasonable things. That's the unfortunate. It is not good at educated guessing. So humans are good at educated guessing. So which is actually funny, because before I talk to you, if you make me hallucinate, before I talk to you, I'm thinking about, is this reasonable what I'm saying? Or will I just say washing machine now? But I had washing machine in my head, but I usually wouldn't say it. And that's the thing. Language models can barely internally think. They utter everything comes out. And then, for example, if you look at how your Gemini or your favorite language model works, you can if you're very fast, you can click, show me the reasoning. And if you then read these pages of reasoning text, you will find half of that is, oh my God, what kind of nonsense is this? And then it filters itself. Like it summarizes and it gives you an overview and it queries itself and it does all of that self-improvement. But it's very much like humans work internally. Make sense? Okay, cool.
Let me to have a proposal.
Yes.
Because really your talk has a lot of questions, but
we are out of time.
We have just now the lunch because they waiting us the people for the lunch. Yeah. I propose the second part of your talk. If you like, we have after the lunch we have Herelle that is coming. Then a short talk of Oier. Then my proposal to have a second part near to an hour at 4:45. We have you have at this time the thing the groups, but we can change and to have the second part of Torsten. Can you this afternoon?
I can. I don't know if the
I think it's very interesting.
Because you are in slide 10.
We're in slide 10 out of 40.
You are in the slide 10. I think it's 1 hour later. It's better to continue. Do you like?
I'm fine. Again, I don't want to bore people to death here with this.
If you are agree,
but I don't have to go through the slides. You know,
we should do the group work by the second part of Torsten, and you are connected and you work along the weekend online the teams. Do you like the option? Yes. Torsten, thank you very much.
Right, sure.
Please, we have a long day. We go to the lunch. Go back quickly to start at 2 o'clock and have another session. Okay?
Yeah.
So the next session this afternoon is about our RDA Lab data competition. And before I hand over to Jean, who's leading our data competitions, I wanted to give you a very brief introduction on what RDA Lab is actually doing, because most of you don't know RDA Lab yet. I don't want to spend too much time on this because we're a little bit tight on the timing on our schedule, but very briefly, just who we are, what we are doing, and why we are doing these data competitions. So maybe as an overview, what RDA Lab is and what we are doing. We are a research lab based in Abu Dhabi. We are funded by ADIA, but we are independent of ADIA. So we are our own little company. We have 6 or 7 employees right now, mostly researchers doing research in different fields. I will talk about them a little bit later. We were founded 3.5 years ago, so still very young. I always describe us as like a research startup. The purpose, like why we are doing this, why we set up RDA Lab, is threefold. We are doing research, so we are trying to advance research in data science and AI in different areas. We are trying to educate people, like in the UAE and also worldwide, about data science topics, and we are trying to build global collaborations and networks in that space. And one of these activities for the global collaborations and networks is, for example, our data competition. Some of the activities we are doing in the educational field is like the summer school, for example, the summer schools here in Granada. We are also doing summer schools in China, our seminars, and so on. Maybe quickly about how we are set up. We have an advisory board that is comprised of 12 members right now, and 4 of them have Nobel Prizes. So a very distinguished advisory board. And for those who have been to RDA Lab events, you might have seen some of our advisory board members speaking. I think Miguel Hernan gave a lecture in last year's edition of the summer school. Maybe very quickly about our research focus areas. We have so far 3 verticals. We are currently building a 4th vertical. First vertical is climate science, then we have health sciences, digital economy, and now we are building a 4th vertical, which is material sciences. So everything is AI and data science related, and then in these verticals, this is like our research focus, and then we have 2 horizontals. We call them horizontal because they span across the verticals. It's trustworthiness of AI and high performance computing, or supercomputing. So now maybe quickly about our competitions. Like some of the activities that we are doing falls under our competitions. This is like best paper awards, research grant, if you want to call it a competition, and a data competition. So together with Jean from CrunchDAO, Crunch is like a data science platform for like similar to Kaggle. We've been doing competitions for the past 4 years. So we've been doing 3 competitions so far. This year, just yesterday, we launched our 4th competition with Crunch. It's a data science competition where we usually define like a problem statement, and then teams and individuals can participate through the Crunch platform, and we have a prize pool of $100,000 that we are giving away to the top 10 winners. Usually we have wide participation from all around the world, more than 2,000 participants from last year. The themes are always different from year to year. We had one year where we talked about predicting the market. Then we had a causal discovery challenge, which was very technical. Last year we did a structural break challenge, where you had to detect like you got like a data set, and you have to look at the data set and say like, did a structural break occur, yes or no? And this year we are advancing that structural break challenge to the next level, bringing it to the next level where you get like a live data feed, and you need to decide at every point in time whether a structural break has happened or not. But I will let Jean explain more about this in the next session. Maybe very quickly about our other activities. What else we are doing other than summer schools and data competitions and research. We host seminars once a month, so if you're in Abu Dhabi, you're welcome to join our seminars. You can also join them online and just dial in and listen in. We usually have one of our fellows or other researchers or even an advisory board member giving a 90 minutes or 60 minutes presentation with Q&A, similar to the individual sessions here at the summer school. We do workshops. We had one with the Santa Fe Institute just recently in February in Abu Dhabi. We have our annual symposium. It's a big scientific academic event that happens once a year in Abu Dhabi in October. So if you want to attend, save the date. It's in end of October. We do summer schools, as you're aware. This picture is actually...
It's okay. It's in, no, but...
Let's see. So we do summer schools here in Spain and in China. And then we have some youth programs where it's more targeted towards students in the high school age, and we offer internships if anyone is interested in interning with us. Yeah, never mind. Never mind. I'll hand over to you, Jean. Maybe one last thing, if you want to stay in touch with us and learn more about our activities, please go to our website, ardialab.ae, and then under news, there's sign up for the newsletter. And if you enter your email address, you will also always be informed about our activities and what we are doing. And that's it. So no, it's fine. I'm handing over to Jean.
Oh, perfect. All right, good afternoon, everyone. It's amazing to be back here. I think I see some friendly face from last year, which is very good to see. I'm just sorry you're going to have to fight two things today. I lost my voice in my plane from New York, and I have a very bad French accent. So sorry if you don't get me. That's two obstacles in understanding what I'm going to present today. But we have some good slides and a lot of content that you guys will be able to go through. So quickly, I just wanted to know who was here last year, so I just know how deep I need to go. Okay, only a few. So I'm still going to show as much as possible. Quickly on myself, I'm the founder and CEO of CrunchDAO. I want to quickly tell you the story of that company so you guys understand where we come from and what we expect from you. And so originally, I was building machine learning models in the insurance industry, especially risk models. And when we exited that company, I decided to launch a long-short hedge fund. So for those of you who know what it is, it's a systematic algorithm that can invest in long and short positions. And when I started to do that, I just realized that financial data was much more noisy and much more difficult to use and to model than what I was seeing into the insurance industry. So I ended up struggling. It was extremely hard. My model could not predict anything. It was overfitted to hell. So I decided to try to find some solutions. And the solution I found was basically, how can I increase the size of my team? And can I eventually try to find a lot of people outside of my team? So I launched CrunchDAO, which was a data science platform on which I was publishing the data of my hedge funds, so my investment strategy. And anybody could come and build the models on top of my data in order to improve what I was capable of doing internally. And I realized quickly that actually people outside of who I was able to hire were much better at building great mathematical models than me, because I was finding statisticians, mathematicians, data scientists, ML engineers, enthusiasts like you all over the world to build on top of my data. And I quickly realized that I better just focus on building a machine that allow me to gather more intelligence than actually using this intelligence. And this is how I met with actually RisCanvi and the rest of the team that wanted to also increase the horizon of intelligence that they were capable of tapping into. And so it's pretty much why we organize these competitions every year. We decide on very difficult and very hard scientific challenges. And we tap into the world in order to get proposals and piece of code from you and from people all over the world. And what is great is that it works pretty well. We now have about 11,000 data scientists over the world that have been competing on the platform. I call them AI experts, but some have PhDs, some are just enthusiasts, some are undergrads, some are just engineers. But anybody can basically participate and try to solve these problems that we face into the industry. And obviously, there is always a pool prize. There's always a bit of money for you at the end in order to get, in order to win something for the amount of time that you put into the problems on Crunch. But what are we going to talk about today? I'm going to show you a bit about the previous competition we organized with Idea Lab. We're going to talk about structural break. So I'm going to introduce you to the subject of this year's competition. What is real-time predictions, which is what you find in the industry and what you find in real problems. There is constraints of time, there is constraints of memory, and constraints of code that you can use. Then I'm going to talk about the scoring of the competition. That's from part 1 to 4. This is going to be about 30 minutes. And then in part 5, you're going to have to take over and you're going to have to submit something into the competitions. But no worry, I'm going to provide you with a baseline, a quick starter, a Python notebook that will be very easy to submit. If you want, you can improve, or if you want, you can just submit that. But the second test, who can code in Python in the room here? Okay, so almost everyone. Who has Cloud Code installed on his machine right now? Okay, cool. So we're going to do both. I'm going to show you how to submit with a notebook, and then you'll be able to submit with Claude as well. We have skills and etc. All right, without further ado, let's go. Last year, Amélie mentioned the previous competition we had. They are still available, so if these subjects are interesting for you, go on CrunchDAO.com and you will find documentations and notebooks around this subject. 2023 asset rankers. So Amélie talked about predicting the market. It's actually trying to predict the relative performance of assets. You know, it's very hard to predict prices because they are very noisy, but what is a much simpler problem is try to rank the performance of assets, you know, because in that case you don't need to predict the price, you just predict relative performance. And so out of ranking then you can build portfolios, and this is what we use, for example, in my fund. We build rankings of investment opportunities, and then we build portfolios out of this ranking. There is interesting papers on that. If you want to know more, I can give you more, but a lot of information is on the platform. In 2024, we worked with Adia and the 2021 Nobel laureate Guido Imbens, that is an expert of causality. So you guys probably know about causality. I mean, everything is in the world. It's trying to find relationships that don't rely on correlation, but more on trying to really make sure that variables are connected. They are not just associated by covariance or correlation. Very interesting work, still available on the website. You can find a lot of things. And last year, we worked on structural break. So I'm going to present structural break directly so you guys have an idea of what we did last year and what is expected from you this year. Just before that, we just launched the competition yesterday, so you are not coming in late. It's going to be open for the next 4 months, 5 months actually, all the way to Adia Symposium in October. You can submit until September 17, so you have all summer to find something and try to be good. The final evaluation will be end of October, and then if you're part of the lucky ones, you'll be able to present your winning solution at the Idea Lab Symposium. And this is an amazing opportunity because you've seen the quality of the symposium. You can get some Nobel laureate to hear about you, to listen to your solution, to see your models, and the whole industry is basically really looking toward this symposium. There is so much innovation every year. It's just great. In terms of bounties, there is $100,000 of rewards for the best solution, $40,000 for the top rank, $20,000 second, $10,000 for the third position, then $5,000 each all the way to 7, and finally $3,500 each 8 to 9, and $3,000 for number 10. So you just have to be part of the top 10. You don't have to win. There is potentially a reward for everything, aside from learning a lot of things and figuring out a very important problem that we find everywhere in the industry. You can compete in teams. This is happening a lot. I highly recommend you forming teams. As you see, the top winners from last year's worked in teams, sometimes big teams, right? So Alphabot, for example, is a team coming from Brazil. They actually run a hedge fund, extremely successful hedge fund at the moment, and they use structural break in order to detect when agentic solutions are out of regime. And I'm going to explain you that more in detail. So they are extremely skilled. That's why they actually won. But their solution is open source. So I would highly encourage you to go on CrunchDAO.com, choose the competition, click on the little documents you have here, and that will lead you to their paper. You can read their paper. All the code is public, so it's up to you to be using this in your own projects. The team behind the challenge. Obviously, Amélie, big member of making this possible. Then we worked with Marco Lopez de Prado, or Simon, Alex Lipton, Emanuele Oliveri from Adia, Vincent Zenekan, Roman Vlazu, and Kushik Balasubramanian. So this is all the people that have been preparing the data, looking at the challenge, and this would not be possible without them. So I really want to thank them a lot. All right, so what is a structural break? So a structural break in a time series is defined by an explicit alteration of the underlying data generating process, which means that you are looking at a time series that suddenly it's not produced by the same data generating process. So something fundamental change behind this line you're looking at. No matter what this line is, it can be price of a stock, it can be how much CO2 has been released in the air last year, it can be the temperature of waters, it can be even the way a bridge is shaking, after 20 years of existence because concrete is deteriorating. It can also be, the rhythm of your heart, how much oxygen is present in your body. That's the beauty of time series. You'll find time series everywhere. I know we talk a lot about LLMs recently and large language models. Well, these models can already process time series. They can help you produce great solutions to look at time series. But time series is really one of the most fundamental bricks in data science, statistics, machine learning, and AI. So concretely, what is? So let's say we have a data generating process, a very simple one like this one. So here we have a value in time that is basically growing or decreasing according to a few variables. So we have a constant plus an amount of noise, which is epsilon here. And you see that by adding this constant, which is here a positive constant, 0.1, plus an amount of random white noise, we get a time series pretty much like that one. Now, what happens if in the middle of that time series we really change this equation and we decide to add this time a bit more noise and change the amount of, and change the constant here? Well, we get something completely different. So this is what we try to detect by looking at all these time series. And sometimes these time series, you don't understand completely the system behind it. If you look at the price of a stock, it's basically all the available information to all the participants of the market. It's an extremely complex problem. So there is no way for you to get that very simple equation. So the only thing you are left with is this time series that you can observe and eventually try to predict when this time series is not acting the same way. This is a structural break. That's what we want to predict. And if we get good at that, then this type of algorithm can be used everywhere. And we can improve a lot of fields, from science to medicals. A few examples of places that I just mentioned. Regime shift in markets. You probably heard while you build a model in quant finance, maybe this model is not going to work when, I don't know, central banks are changing, economical policies. Suddenly you have different level of inflation, political event, Detroit of Hormuz, these kind of things can change, have an impact, change the regime. And when the regime changes, your model will be trained to look at something that now is completely different. Your model will blow up, it will just disappear. Vital sign drift, so ECG from rhythm change, brain activity, predicting seizure in advance, infection rate. In healthcare, there is a tons of use case. In industry, I mentioned bridge, but equipment wear, like the temperature trends, weeks before a structure is about to fail. And finally, climate, of course, long-term shift, the temperature, the daily rainfall. There's so many use cases. So please look at time series because it's really an amazing field that even if it seems simple, it's actually extremely complex. And it's usually like that. The simpler the problem is, the harder it is to build a model on top of it. So we're going to dive into it today. And I'm going to have to drink all the day, so I'm not losing my voice. So last year we were giving you all the time series at once. And this time series had two parts. Basically had one segment on which we were sure there were no structural break. Then there were a second segment of the time series where we were sure there were a structural break. You could train your algorithm on this time series, and you had to then predict on an out of sample of time series if your algorithm can find a structural break or not. This year it's slightly different. We want you to do this live. And so let me give you a very concrete example. This is last year, period 0, period 1. You had a training data set. So you see we had 10,000 time series that each had an ID. Each of these time series, of course, had value. So this is what we mentioned, the data generating process. And then you had two periods, 0 and 1, before and after the structural break. So we also had a training sample that was basically giving you, the labels in order to let your algorithm know, okay, in this particular ID we have a structural break, in this particular ID we don't have. Just a quick check on you guys. Who already trained an ML model in the room? Even a XGBoost, light supervised learning? Okay, just a few. Unsupervised learning as well? Okay, so let me take it that way. When you train a model, you show historical data, right, with an outcome. And you want this algorithm to train on that and be able to detect what you're showing him on data that he never see, right? So you're going to give him the truth in the past with the data, and you're going to let him try to figure out if he can find in data he never see. So X-train, it's what you're going to train on, so that's your truth, right? In the past, with Y-train that tell you basically, okay, there is a structural break in this time series, 10,000, true. Time series 0, it's false, meaning there is no structural break in this time series. You feed that to your algorithm, and we're going to see how. And then you can eventually be able to do that automatically. A very concrete example that I want to show you guys of structural break. It's kind of a funny, cheeky one, let's say. So last year, one of our participants that had very good score in the competition is running this model that he built during the competition. And I don't know if you remember, last year, Trump did a tweet about tariffs. And so he looked at what happened before and after the tweets of Trump. And what happened before and after the tweet of Trump is basically Bitcoin going down about 20% at the same time as a tweet. We talk about 0 minute after. So you see that black line here is the price of Bitcoin here. This is the price of Bitcoin, and this is the probability of having a structural break, meaning the system out there is different. Well, right on the tweet of Mr. Trump, you have a 98% of chance of changing regime, meaning that, okay, whatever you were doing before, you're going to have to do it differently because now Mr. Trump is on Twitter and eventually he's going to tweet things like that. So that's a concrete example that brings it back a bit to reality, but let me get back to you can read the full article if you want to scan okay, let's say, if you want to scan the QR code here. Okay, so what is different this year? This year, we want to do this live. And that was a big problem of last year, is that last year, you can have this probability, but only after the fact. So after the fact, you looked at these two phases, before and after the tweet, and the model gave you a probability of a structural break. But we could not do it live, so we could not predict, this is what we're going to do this year, is that can we predict, here, like 2 minutes, 1 hour before the tweet of Mr. Trump, maybe there is some things happening in the market that we can find inside these lines that will help us to anticipate on this change of regime. Maybe a bit more noise, maybe some insider activity, we never know, with this administration. There could be someone already trading, knowing that Mr. Trump is about to come with tariff on the market. So maybe we could have figured it out. So that was one of the limitations of last year, which we intend to solve in this year competition. And so in this year competition, we give you 2 parts. The first part is an historical segment from that time series on which you can train your algorithm. So on that, you can find what is the average value of the time series, how much the time series is moving every day, what is the standard deviation every hour, every day. You can build all type of statistical tests to know what is the normal behavior of that time series. Then there is an online segment that starts. So in this online segment, we're only going to reveal to you 1 point at a time. So if the points are day, let's say, you can only see 1 day at a time, and you're going to have to give a prediction for that particular day. The reality is most likely be every microsecond, right? Or every second, or every nanosecond, best case scenario. So every microsecond, let's say, we're going to ask your algorithm to give a value which is between 0 and 1. Do you predict that there is a structural break coming in the next point? And basically, here what you see is the simulation of a structural break happening in the online segment. So you see here, for example, we can see that the volatility of the line is way different. Here we really see normal behavior, and suddenly here we see much more volatility, right? Much more noise. Something's happening is different. And so in that case, you would have had to predict, in the base case scenario before, most of the time you end up predicting quite after the beginning of the time series. And so this is how the data set looks this year. You have, again, 10,000 time series to train on. Each time series has steps. That could be second, microsecond, values in these steps. You have these 2 periods, historical for training, and online, where you have to give a value every single step. Okay? The tau here is basically the index of where is the structural break in the training part of the data. So in the training part of the data, your algorithm knows the value and knows where is the structural break. So you're going to train this guy to be able to detect it automatically in the future. Does anybody have a question here? Is it all clear?
Time series is for just a single asset or for the whole market?
So each time series is basically obfuscated. You have no idea what it is. It can be financial. There is 10,000, and you can treat only 1 at a time. Right? And so this 10,000 time series represent all kinds of time series. Climate, weather, financial markets, things I mentioned before. Any other questions? Yeah.
For example, maybe a structural break is a similar of the concept tree.
Say that again, sorry.
Concept tree. Is structural break.
Oh, thanks.
Is a similar of concept drift. Concept drift is a thematic of in a time series try to identify chain of the or distribution of the data.
Yeah,
drift.
That could be. Yeah, drift is a good example. Yeah, basically you have here one approach that could be doing having a PDF, so a distribution hypothesis on where the next point is going to be. The probability of each point being present in the next step. Out of this probability, you can then infer things. That could be an advanced solution. Actually, it's not that easy. Anyone else have a question here? Okay, good. It's important you following here because then we're going to get a bit more in depth. So, what do you have to submit in every step? In every step, in the out of sample, so in this online period, you have to tell us if there is a structural break or not. So it seems very simple, seems very basic. And basically, if you submit 0, it means you're fully confident that a break has not yet occurred. So 0 means no break. 1, you're fully confident that the break has already occurred. So you want to say 1 right after the structure break. Reality is that if the structure break happens at toe here, and this is what you are submitting, right? You don't want to submit 0 or 1. You want to submit a continuous value, so something between 0 and 1. It is more like a probability, not really a probability per se, but it's a value, a continuous value between 0 and 1. And so if you do that, you will basically give a confidence value that a structure break has occurred. And so here you have your submission. You see it's going fast to 1 after the break happened in the time series. And so that's probably a very good submission, right? So in code, it's going to be step 0, I'm submitting 0, step 2, I'm submitting 0, step 3, I'm submitting 0, step 4, I'm submitting 0, let's say I'm submitting 0.2, and then step 5, I'm submitting 0.7, step 6, 0.8, step 7, 0.9, and then I kind of go on the top. I'm sure there is a structure break. And so if we look at this animation again, here is the online section you've seen. And thank you, Emanuele, by the way, if you're looking for this amazing GIF. It really explains everything you need to know. Everything is here. Here are the time steps in the online, and you see at the moment of the structure break, the value you're submitting is going up. So it's going up. Good, structure break occur. I'm more and more confident. I'm super confident there is structure break. I'm submitting 100% now. No question here? All right, it's pretty simple, right? The scoring, how do we score you? We're going to score you on what's called area under the curve. Who already heard about area under the curve? Okay, almost everyone. So basically you try to assess the error surface, let's say, in trying to solve a problem. So we see again the same submission. This is our structural break. So that would be the perfect solution, someone that has 100% confidence at the right time. So you scored against this perfect solution. And your submission was this blue line, and we see that after we went up, then we were super confident. Well, AUC is going to compute that area, and obviously you have to minimize this amount so you guys can actually have as little as possible. All right. Now, there's a little bit of complexity, but since not everyone heard about AUC, I don't want to go too deep into the weed here, but actually this AUC, it's time stratified. The goal is to make sure that there is no way for you to cheat by using, statistics that you would have gathered on the overall sample. And so, just quickly, the way the time stratification is working here is that in this example we have 3 time series A, B, and C, and we're going to all concatenate them so we align them. They don't have all the same size, right? So when we're going to align them on step 0, we're going to look if there is a structure break in any of them. Then let's say there is a structure break in time 1 in the time series B. And you predicted it, and you predicted perfectly in all the other time series as well, then you have the best possible, you have one. By the way, you have to maximize, you don't have to minimize, sorry, that's a mistake. So here you have a value of 1, meaning you perfectly predicted the overall sample. It's basically a way to avoid any cheating, so look into it, but it will not imply the underlying methodology that you need to use. Quickly on the data, you have 10,000 time series in the training set. You have 100 time series that you can use locally in order to test your algorithm locally and etc. Then you have 10,000 public time series that allows you to be on the leaderboard. So all this data is for you to train on.
This is only online. You cannot have it locally. When you're going to submit your code, we're going to run your code against this 10,000 time series, and we're going to put a score for you on the leaderboard. Then at the end of the competition, in the last week, we're going to rerun everyone against 10,000 time series on a private dataset. Why do we do that? We do that because people in this kind of competition are overfitting on the public test, which means they're going to submit so many times, they're going to have a perfect score on the leaderboard just because they brute force what's inside the scoring sample. So there are going to be 2 scoring samples. One during the 6 months, the 5 months of competition for everyone to see, and one is going to run only at the end, which is the out of sample. So when you're going to look at this leaderboard, please don't over-index on people that have 99% accuracy. They're probably doing something extremely wrong. They're just brute forcing the scoring. So be conscious, build your models while being conscious. There is techniques to do that. The cross-validation, for example. So a lot of you didn't build a model yet, but cross-validation is a way to test your model in different parts of the data, making sure you are not learning by heart the data. This is not what we try to do. It's like the best example of overfitting for me is trying to teach a child. What you want to teach a child is to be able to face a situation he never seen in the past and be able to be smart enough to address the situation without having his parents away, right? So you can teach how to do bike, you can teach a lot of things, but then he's going to grow up and face situations that we are not in your teaching samples. And you want these kids to be smart enough to be able to make great decisions in the out of sample of his life. Same thing for an algorithm. You train the algorithm in order for them to be good in the out of sample of their life, not in the past, in the future. All right, how do we submit? And maybe some of you have questions here on training algorithm cross-validation. If you do, feel free. If you have a question at any time, feel free to reach out. So there is 2 functions that you need to submit. An algorithm has 2 phases. There is a training phase, there is a testing phase, an inference phase, let's say. The training is actually optional here. Training will allow you to retrain models on the out-of-sample data, so it's a bit technical. I recommend for most of you to just use the infer function. Infer means predicting. So what happened to the infer function? Well, infer function is receiving the time series, right? It's using your mathematical ideas inside this function, and then it's going to send back a prediction. So it's going to yield a float between 0 and 1 for each of the online sample. So focus on this. There are a bit of constraints in your code, and especially on the library you'll be able to use. If you want to use very special libraries, you have to whitelist it. So just come on our Discord server, ask for a whitelisting, and you'll be able to do it. You have limitation in compute, because obviously a lot of you are going to come and just want to submit a large language model inside the competition. If all of you do that, then it's going to cost a lot of money to Adia Lab, so we had to limit a bit the resource you can use. So you have 15 hours per week of run of your code on our servers. And you have to be conscious of time, because we're working on live time series here. So if you have a very intelligent model that needs 1 week to actually run, then, you know, Trump already tweeted, the price is already down and up and 3 times. So there is a constraint in how much intelligence. And this is happening a lot in streaming data, because, for example, we were working on this microsecond data last year. So every microsecond you have a new data point. You cannot really run complex model in that amount of time. It's a microsecond. And if you want to be part of the market at every microsecond, you sacrifice a lot of intelligence for efficiency. And this is often what's happening in production. You know, everybody would like to run an algorithm for 20 days, but then it's too late. So you have to compromise. It's pretty much what you have to do here. So I also recommend you for time series to use pretty simple things. The simpler the solution is often often the best. Going too complex here is maybe going to push you into a more noisy environment and probably more overfitted as well. Do we have any question? I'm afraid I don't want to put you to sleep, so just few more slides, and then you're going to have to submit. You're going to have to use your computer. If everybody has a computer, please put it out if you didn't yet. A few more texts. I'm not going to annoy you with more mathematics, but I'm going to give you a quick starter, so a Python notebook that you can all execute. That's going to show you a very simple solution to this problem that you will be able to submit, so you'll be able to have a score in the competition. So this is how it works. I don't want to go too much in the code neither, but basically some of you may probably have heard about exponential weighted moving average. Who already did? Exponential moving average. It's happening a lot in trading where you want to compute an average value, but this average value, you want to weight it by how old are the value you are taking in consideration for this average. Makes sense if I ask myself how much food I can eat and I take in the average, how much I was eating when I was 5, it's not going to work, right? So for, trying to average how much food I can eat today, I better use, the past 3 years like that. For time series, you will use maybe 20 data points before, 100 data points before maximum. So if it's day, second, depends. So that's what we do here. First, we compute an exponentially weighted moving average. So the exponential part means that the closer the value is to the present, the more weight we're going to put into that value. So not only you are reducing the amount of value you're taking in the average, but you also give them weight in time, meaning how much I eat yesterday have a very high weight, how much I eat 2 months ago had a bit lower weight, and how much I eat when I was 8, it's not even taken into consideration. And then we compute a very simple, it's called z-test, so it's basically trying to figure out how much the time series is different from the previous step. So it's very basic, it's pretty much what we do every day, just by looking at the time series. We do that on our head, it's just how different it is. It's pretty simple. And so this is the submission platform that we're all going to use now. Just before we go there, I want to propose you a few potential submission that may perform very well. So cumulative sum and the deviation of standardized residual, so have fun with that. Running variance, tail mass changes, tabular classifiers, I highly recommend that. That's one of my favorites. I know some of you used it last year. So you turn the time series into a table and then you build, you can launch an XGBoost or like GBM or trees model to the time series. Autocorrelation, of course, likelihood ratio. It's also something pretty famous. All right, for the few crabs I've seen here, can you guys scan this QR code? Because it's gonna directly send you to, for the one that want to use Claude, by the way. Let's say you're very bad at Python, you don't want to code, you just want to have IDs and ask Claude. It's very fine. We support that. You can do it. And your idea is valuable, sometimes more than things, more than you think. So we have a full tutorials with skills, meaning that once you would have run these tutorials, and I'm waiting for everyone to have it. I see there's still a few phones. I recommend for you to maybe do it today. Maybe today is a good day to install Claude Code on your machine. But I'm not a security expert, so make sure you can do it. It's your things, and you know how to, take care of that. But if you want, I can help you install Claude and compete on Crunch. It's like extremely easy. All right, everyone have it? So what it means competing with Claude, it's going to be basically as simple as that. Once you will have Claude installed, what I literally say, Claude, is I want to compete. I want to compete on structural break 2026 from Crunch. Claude is going to automatically find our skills files. The skills files will give him everything he needs to know for being a good competitor, and then I'm going to tell him a classical one, make no mistake, that works usually, and make me win, let's say. That's literally how you can compete today. It's obviously not going to yield you very far, but then you can ask Claude to read specific papers. You can ask him to read specific books about it that you find and combine the model. So it's happening. He crunch. Okay, he's competing. Very good, thank you. Do you want to allow Claude to get this data from, this is basically our competition website, so you already find it. Oh, thank you, let's go. It's going to run for the next 30 minutes, and maybe by the end of you trying to submit, I will have submitted with Claude. Maybe I have a better score than you. I don't know. Probably. If you submit the quick starter, probably. It's going to take a bit of time. Remember that you will need you will need an account, so you need to pay Perplexity when you use CloudBot. So that's the only thing. It's not a lot of money, but if you run something crazy and you let it run for 1 month, then it's going to cost you a bit of money. So be conscious of that cost. Okay. All right. So without further ado, I'm going to show you how to compete now. So everyone, get on your computer now, and I want you to go on the CrunchDAO website. You have to do it live, guys, because I'm going to take you through creating it. So I want to see your hand tapping. Otherwise, it doesn't work. Actually, just go on hub.crunchDAO.com. And let me do it on a private window so I can actually take you through the full process. All right. I guess everybody's trying to access the website maybe at the same time. Maybe that's why. So if you go on hub.crunchDAO.com, you will end up on the competition platform. On the top, what you see here, it's all the money that is being currently won by all the participants that are currently participating. So in all the competition we're running, you have potential to actually earn a bit of money every day. Actually, some competitions are every minute or every second, you can earn a bit of money. That could be a side hustle during the summer, I don't know, aside from the $100,000 from Adia, which is obviously much bigger. It's like a good way to use your intelligence, every day. So you guys are going to have to log in, obviously. So far, nothing different than a traditional website. Enter your Gmail account. And actually, I will have to sign up. So let me sign up. So my name is Jean. Herelle. What is your country of residence? I say United Arab Emirates. And what is my email? I'm going to add another one. Creating an account. When you create an account, you're going to receive an email on your mailbox. If you do it at the same time, with a verification number, let me fetch it here. Here we go. 93307. Here we go. All right. If it's your first time on the platform, you'll have to answer a few questions when you're going to enter the website, which is what is your university, where are you living, what is your experience with data, etc., etc. That's like 5 questions. You should be pretty fast. Then, this is your dashboard. This is basically where you see how much money you've been making. This is it. You're going to receive, notification when we have a new scoring, new competitions, and etc. You'll be able to have your contribution here, and basically this created a new website, a new thing. And then if you scroll, you'll see the current competition. So you click on Adia Lab real-time edition, the structure break editions here, and then you will have to accept a few rules that are very important. You basically you agreeing to the terms of services, but you also agree to the chart of the website, which is we want to have impact. You want to be a fair player. You don't want to cheat neither. You cannot have multiple accounts trying to submit at the same times. Don't try, we usually figure it out. You want to be a fair player. So once you accepted that, we're going to ask you to create your first model. So creating a first model at this stage is just naming it. Then we're going to push code into it. So let's say I'm calling it Agile Lab Summer School Demo. All right, create. Oh, okay, I just created too many, I think. Too many demos. All right. So once you created your models, you end up on this submit interface. I encourage you going over the overview first. So it's pretty much what I told you guys. Again, in written content. So what is the time series? We've seen all that. The data set, the online, the different things, the scoring in details, all these kind of things. Now, down the page, you'll have the quick starters. Quick starters is really where you guys are going to get some free code and a way to submit by yourself. So if I click on quick starters, it's going to open a Google Colab. And which of you have already used notebooks in the room? Like, do you? Just one or two? So most of you are using notebooks for the first time? I don't believe it. Yes? Okay, cool. Then it's a good time to do it. Aside from Claude, this is important. So it's basically an executable environment. Let me see. Just charging. And I'm going to use my own account. The Wi-Fi is a bit slow, but here we go. So basically here, same thing. I report again all the consideration you need to know to participate. Then if you scroll down, you have basically where the getting started part is important. So you can collapse that parting. So how to get started, we just have to identify you so you can download the data. So if you click on that link, it's going to redirect you to your account. And from that account, you can click on the Reveal button here. That will give you your tokens. So this is how we identify you, how we let you get the data. Click here, and then you can just pass your token into these cells. Now, how do you execute cells in a notebook? You can just click on the little live button over there. Click on live, and it's going to execute the code within that notebook. Run anyway. And so here what we do, we install the Crunch CLI. The Crunch CLI will let you access everything, let you access the data, let you access the scoring, being able to submit under your name, etc. And so since the internet is a bit slow, the download of the data may take a bit of time, but it should be fun. So while we do that, I'm going to go down a few cells. Here we're just installing a few basic Python library that you probably already heard of. And then we import the library that we actually just installed. And from that point, basically, I can just load the data, access the data, and start working into this notebook. Okay? This is just some visualizations, functions. Don't pay attention to it. The important part will be here. So now we already connected ourselves. We identified ourselves. We can access the data securely. It's the moment to build what we just described. exponential weighted moving average, then a z-score on top of this EWMA in order to predict if this time series is different in the current data point than in the past. So we're going to jump over the train function, we say, and go straight into the infer. And so here, you'll see in Python code exactly what we just described. So we're going into all our historical data sets, all our historical time series, one by one. So for X historical, X online, the two parts that I described in our total data set, I'm going to build a few features. So the first one is just turning it into an array, specific type of data format in Python. Then we build an average, a mean on this time series, only if the length is not 0. Then I'm building a standard deviation. Then I'm finding the max. Then I'm building the z-score for every point, etc. So let's say you would have wrote that. That is your solution. You're happy at every new time series you are yielding a score, so value between 0 and 1. So you did the job. You can run a local test by running this crunch tool that test. It's going to automatically find your infer function inside the notebook and run a test and basically give you the prediction. So here we did prediction for the time series with the ID 10,000, and we will be able to compute. You can also run this to get the score, so the stratified area under the curve that I presented to you earlier. And if everything goes right, basically, you did the job. So here you just have to click on File and download your notebook. So here I'm taking it out of the Google Workspace, taking it locally, and I'm going to now submit it on the platform. It's very simple. You go into Submit. Here you have a notebook submission option. Select your notebook, hit Enter, add a little description, so demo some school, and then I can submit to Locked-in. Locked-in was the name of my mother, that's why. Here we go. So now it's processing my notebook. It's looking at all the code you would have written. It's going to look at your libraries. Are you using libraries that are allowed? And then it's going to convert your notebook into code on our server so we can run it on the scoring sample. So here we go. Step 1, step 2. I'm going to pass it so we don't lose too much time here, but once you would have automatically passed all these steps, you will end up on this page where you have a submission that would have automatically run on the public data so you can get a score. So you can see my submission here have been run in the CrunchDAO servers. So you have the logs of what happened on our servers. It's basically telling you everything went fine. If it's green, good. If it's orange, still okay. If you have a red tag on the left, maybe something broke and you have to figure it out. But with the submission I just gave you, if you submit this notebook like I told you, you will see your name on the leaderboard. And so right now, we already have 17 live models since last night, so it went pretty fast. And where am I? I think I'm already lost. Yeah, okay, I'm here. I'm 15. So I'm not doing very well, but hopefully you'll see your name right away. You will see your score. So here is the latest submission array under the curve. The best, the better. And since you submit several times, we also give you your best score over all your submissions. And this is what we use for your ranking. Here it's number of submissions you do. It's a way to show everyone when you are trying to brute force the algorithm, because some people will end up with 5,000 submissions here. You know you cannot trust them. They're trying to retro engineer something. That's about it, guys. Here you have everything. We're running a bit late. We have 10 minutes, so I guess you won't be able to build something crazy. But if you want to use this 10 minutes to submit something, at least it puts you in the race, and you will receive update, and you can start crunching. One quick thing I want to show you is how to build a team. Let's say you feel you don't want to do it alone. You don't have friends around you. You can actually do it with other people within the community. So I can create a team by just clicking create here, and then I can make this team open to anyone, and people will request to join your team, or you can request people on the leaderboard. So if you go on the leaderboard, let's say this guy is actually pretty good. Let's see what Gaurav is doing. And basically I can take his username, and then in the team, when you create your team, they ask you, do you want to request someone to join your team? Then you can put this username, the guy will receive a notification, you can say yes or no. And guys, that's about it. So you guys are all set up to compete now. The rest is up to you, I guess. Do you have any question? Do you guys want to jump into it for 10 minutes? And I can go around you and help you if you want. We do that? Okay. Perfect. Well, thank you so much, guys. And in that case, I'll go around. Thank you. You have actually... Yeah.
What's the average, the teams, the average number of people?
Average number in the team.
To our students, if they want to
Yeah.
participate with friends.
So yeah,
What's
if you go...
the usual average of people participating in a team?
Yeah.
Or what is your suggestion?
So we have...
Let's suppose that people here from the summer
Yeah.
school, that they are working now in group, but in
I
other
guess-
topics, if they want to
Yeah.
participate. What is your suggestion for a good collaboration among them?
I think it's more of a social question. There is this theory about management that you cannot really collaborate very well with more than 7 people. Like you kind of lose track of what's happening. That's why we ended up building organization with like teams that have this size. I would not recommend to be more than 7, honestly, except if you already worked with these people in the past. I think a good size is 3, 2 or 3. The good size, I think, to really understand what you're doing and not ending up with too many things. Some people, you see this big team, they are 5 in the team, but they're actually working every day in this hedge fund together, so they know how to collaborate. I say 2 or 3 people is good. Then, if you put your university here, you will also end up in the university leaderboard. And actually, we have you guys somewhere since we have students. We have like.
I agree with you that
we have
2-3 people is good for collaboration.
Absolutely.
More people in more complicated collaboration. You
Absolutely.
Right.
Yeah, you see the team are usually 2, 3, and some people are still alone in their team. They're just trying to get people in. So that's it. All right.
Any question? Any comment?
Very
Okay,
good then.
thank you very much.
Perfect. Thank you.
Because we have the different section, let's go just now to the coffee break, and we went back at quarter to 4 to start. We advance a quarter in order to have time, because we have the presentation of Oier and later the Torsten presentation, the second part, okay? Then we have 25 minutes for coffee, please. Well, let's go to remember that we start 10 minutes before. Remember that we have after Oier the second session today with Torsten, the second part. Well, here really I'm pleasure to introduce the talk of Oier. Oier is a PhD student in the industry and was working with students in a summer school project with other colleagues from Abu Dhabi, from Bilbao, Jesus from Granada, and no more. 4 people, and they choose a project about explainability, governance, and trustworthy. And the idea of them was a very interesting idea. He will explain was to pick up a real problem and then to use the real problem to conduct or to prepare the proposal. Well, really a very good proposal. And after the proposal, I proposed them to continue working in the proposal. They were working, I remember when it was submitted, around November, the paper. Yeah. Around November, more or less, they were working after the summer. Jesus was here, the author. Jesus is there. And they were working in the paper, and it was submitted in November. Received a major revision, normal major revision. Well, they were working, and then I was supporting more than with the discussion with the reviewers, and we decided to have the presentation because it really was a necessary work, and really between was agreed to have the presentation and the organization, the final organization, where they received the final acceptance 1 month ago. Yeah, one month ago was accepted the paper. The referee was happy with the outcome. It was not so difficult to update the paper according to the reviewers' comment. They were very positive and constructive opinions. Really, the paper was improved, and finally we are very happy because it was affected. It was the first paper of a student collaborating in the summer school. Some students were collaborating more at the beginning, others finished the paper depending on the time. There was a mixed team with different knowledge from philosophy, Jesus, computer science, Oier, economy,
You're starting to say my slides, you know?
Sorry, because go ahead. Sorry.
No, don't worry, Paco. First of all, Paco, thank you for your warm words, and of course, thank you, Amelie, and the organization for the opportunity to be here. As Paco mentioned, I am Oier Mentxaka, and I do my PhD here on AI auditing in DASI. Oops. And today I want to open this session with the question you have here on the screen. What if your freedom was decided by a secret algorithm? Well, this is not a hypothetical question. It already happened during a lot of years here in Spain, and the system who wrote the question was called RisCanvi. This presentation, as Paco introduced, is about how we managed to get from the summer school project into a Springer Nature scientific paper. Okay. Sorry. Okay. So everything began last year. Last year in May. And we started collaborating on this Idea Lab summer school when an uncomfortable conversation appeared on the table. Nacho and Nuria did really well with the work teams, and sat in the same table, really different mindsets. We were a philosopher who seated there in the back part of the room. Me, knowing auditing techniques, social scientist, which is not today here, and other 2 ADIA mates that were computer scientists. So you can imagine that very different mindsets and very different people were sat around the same table with the same question. Can we trust an AI that decides about our lives? And that was the beginning of the Summer Schools project, this question. We started thinking about different use cases. You may have heard about Compass in the US prison system, or about some hiring algorithms, such as the one Amazon had with discriminatory outcomes, or even with the credit scoring systems on the financial sector. These were some use cases we thought about, but all felt really distant to us, although they were really concerning regarding their opacity. Gathering on the internet and searching for a bit of information, we suddenly saw RisCanvi. RisCanvi is a prison risk assessment tool that has been using in Spain since 2009. So it's for 15 years in Catalonia. In the high risk scenario, prisons really are. And this system was taking decisions regarding real people having lots of social consequences and possibly enhancing lots of bias and discrimination to people. Our approach then was to use this concrete use case, RisCanvi, to reveal how corporations, companies, governments, or anyone has opacity on their systems. We had somehow here on the left RisCanvi, a deployed legacy AI system in use. We had a greater problem there, which was the algorithmic opacity compounded by the corporate opacity, and we had finally the possible solution. We managed afterwards, this is part of the paper, to create this framework based on the AI Act and ISO to try to make this system explainable. So our question was, how do we make this transparent? We were not trying to change it from scratch. So let me get deeper in what RisCanvi is. RisCanvi is a prison assessment system which will provide whoever it uses a risk score. So we had a bunch of data provided by the prison's staff and gathered by them. A black box logistic regression model with which was going to give a score to a person thanks to an input, and the decision taken by a judge. The thing here is, or the key in this slide is that we had a black box model which was given a score. Those phrases may sound a bit worrying because who knew about RisCanvi? Technical staff knew about RisCanvi, but a little bit. Judges knew about RisCanvi, but they didn't know how it worked. Inmates even didn't know what RisCanvi was. So the only ones knowing a bit about the system were the developers, because they knew how did they model it. So, and that asymmetry is the problem we found on this concrete use case. So let's go and try to understand a bit more RisCanvi. RisCanvi is a system who had 106 candidate factors drawn from similar systems all over the world, mainly from the Compass US system. And from those 106 pool factors, 10 of them were used for the screening phase and 43 for the full assessment. Since RisCanvi has two models on it, although we are talking always about one, because it's the same with different configurations. Something tell us that the developers of RisCanvi were somehow concerned about the ethical implications this kind of system may have in society. So they decided to have 4 protected variables on their system, which were age, sex, criminal status, and nationality. Okay, RisCanvi then, as previously mentioned, is split into 2 little models, RisCanvi Screening and RisCanvi Complete. And how RisCanvi worked is clearly seen here. Every inmate was evaluated as soon as getting into prison with RisCanvi Screening, and if the result of RisCanvi Screening was, if the prison was tagged as as high risk prison, RisCanvi Complete was used for him. If not, it was only used to RisCanvi Screening, and of course this study was repeated every 6 months in order to try to change those status or those evaluations from inmates. Okay, I want to ask you a question here on this slide regarding the initial 10 variables I was mentioning before. These 10 variables are the ones used in RisCanvi screening, and I want you please to try to give me if you find anything interesting on them, something remarkable. Any ideas? Please, Nuria.
For example, the lack of financial resources.
Okay, that's a good one. Any other idea in the room?
Also, the absence of family or social support, since it can reveal social status, like low income or stuff like that.
Okay, you are on the good way. Any other ideas? Okay, hold on. That thought. We will come back to this afterwards. Okay, RisCanvi screening, the only thing was, the only aim of RisCanvi screening was to see or to get an indicator for these three things we see here, okay? The prison system wanted to know if there was going to be any kind of self-violence risk or institutional violence risk or breach of sentence condition risk for every inmate. And the only answer the model was giving was if it was high or low. Neither numbers, only two tags. It was a binary answer. The thing is that RisCanvi was thought to be a human-in-the-loop system, but in reality it wasn't. Only the 3% of the results were overridden. 3% in 15 years were overridden by professionals. What does this mean? That the 97% of the rest of the results were just approved without knowing. Not because they were good results, neither because they were faithful results. It was because no one could challenge the proper system. I mean, the system was only giving 0 or 1. And you cannot contest what you cannot see. Okay, these are some of the variables used in the RisCanvi full version. There were 5 sets on it, and I took here some of them in order for you to tell me a bit more now. Anything you see even more worrying than before? Go ahead.
Education level.
Which one, sorry?
Education level.
Education level, okay. Why?
You cannot judge based on education level if somebody...
Okay. Okay, I agree with you. Any other? Carmen?
Distance from residence to prison.
Okay, distance from residence to prison. That's a good one too. Any other ideas?
Low mental ability.
Low mental ability, okay. Any other?
Being a member of a social vulnerable group.
That's the one. We can see here that there are 2 groups there, which are biographical and family and social, that are taking into account not actions, but facts. Things that were from those people in their lives because they were born to in a place. And if we count the whole 43 factors of RisCanvi complete, we can see that only these 2 subsets were taking the 40% of the whole data set when taking decisions. So we might think about it as, well, completely biased or possibly completely biased. RisCanvi complete was a bit more accurate regarding what its outputs are. With this, prison system wanted to know about risks on prison management. Well, not risks, sorry. They wanted to somehow give privileges to some people regarding the risk factor. And those factors were risk management, conditional release, prison benefits, or rehabilitation plans. And in this case also, we were getting only categorical outputs, which were high risk, medium risk, or low risk in order to get any of these privileges in prison. Again, only the 5% of the results were overridden. So we could say somehow that, summarizing, that every decision taken by the machine was accepted with no discussion. So let's summarize a bit. We had a system that used lots of controversial data. We already seen the 40% of the data set, or of the attributes of the data set. A system was almost never challenged, and it directly shaped someone's life. So here, our colleague and philosopher Jesus started to think about, his worries, of course, his professional worries, and he came up with 3 different ethical repercussions. Don't correct me if I don't say it well. If I do not, if you want to come here and say, okay? And those ethical concerns were the 3 ones we have here in the screen. Discriminatory outcome, lack of autonomy and individual agency, and the opacity and the collapse of accountability inmates were having. And yeah, these were not hypothetical harms. We already have seen them. Okay, let's get into the discriminatory outcome part. Can you read the inputs there? Those you have been mentioning during the last slides may appear there. We are talking about poor childhood adjustment, about criminal history of family. Family? Why? I mean, lack of educational level or financial hardship. I mean, these are variables that are not showing someone's actions. These variables are showing structural disadvantage. They're showing poverty, they're showing social isolation, they are showing marginalization, which is also okay, it's a fact. But does that really matter when regarding freedom or releasing from prison? The thing here is correlation of data shouldn't be affecting directly to the answer of this, because it's disadvantaging people's lives, not people's actions. Okay, the second one was the lack of autonomy and individual agency. I want you to please take a look at these 2 pink boxes, because these are real testimonies from inmates, which said, you don't know the question asked, will populate the database translated into parameters. No one tells you anything. You answer innocently without realizing. Without realizing what? That their lives could change depending on what they are answering. And the other one said, I didn't know about RisCanvi during my time in prison, which also concerns or at least shocks us. So what does this, what does this corporate, because this is a corporate opacity, leads to? To an awareness of those inmates, and of course to the loss of their agencies. This is not an opacity as when we were the same opacity as the previous one. The previous one was the algorithmic opacity. That one came in directly from the algorithm used. This is even worse. This is about corporate opacity. The prison wasn't saying anything to anyone, and they were using a system without knowing anything about it. So imagine an inmate on prison willing to study a new degree or willing to do anything else to try to change that kind of factor in the further 6 months. It would be impossible. I mean, their effort becomes short in dark as soon as they were doing anything, because some of those attributes were not describing actions. And the third one is the lack of opacity and accountability. I have a little question here also, which is, who is responsible in case of RisCanvi commits, not a crime, but it commits an error? Who do you think it is? I mean, this is the main answer, no? Jesus showed me, it's called the problem of the many hands. Because developers could say, we only build the system. Lawyers could say, we only follow the system's prediction. Or the prison staff could say, we only gathered the data, we did nothing else than that. So that responsibility starts deriving into nothing, because no one is responsible in the end. And this brings lots of problems to society, because, I mean, oversight here is completely degraded. And and it also happens to an external auditor. If information is not given to them, it's impossible to see what the system does. And of course, due process is abstracted, as defense lawyers cannot contest the system's answer either. I mean, how can you say, okay, yeah, you have an answer, but why do you have the answer? Why are you condemning my inmate due to that, my client due to that? Tell me, Nuria.
I was wondering if, I can remember the name of the, if CrunchDAO, blah, blah. If CrunchDAO, the framework, I can remember the name, was designed to be a human-in-the-loop framework. Wasn't a human in charge of supervising the outputs? Because if it was, this human should be the responsible, right? Or I'm not a judge.
Yeah, I mean, what we read in the what we read in the audits that were published on the internet was precisely that: who's responsible, the one seeing and the one taking the decision. The thing is that you don't really know, and you don't have any kind of information but 3 categories: medium, high, or low risk. So if it's, if you have, let's say, a good result somehow, why are you challenging the system? I mean, but the thing is, if someone was changing, those changes were never going to arrive because, well, some attributes were there giving more weight to the decision. So, how can we translate this to the legal aspect? Okay, RisCanvi is really close to the red line between the high risk programs and the prohibited practices, because Article 5.1.d says that no one can be profiled due to their personal proxies. They cannot be profiled due to biological or social activities they have. And so we would say that this system itself, it's a prohibited system. Our position when we wrote the paper was to change it a bit. We decided to just remove those 2 categories on the 47th dataset, so we could translate RisCanvi into the high risk set and follow working with it. And well, it didn't either pass anything as it was. Only removing those attributes wasn't enough. They needed to have risk management systems, as the article then says, transparency, human oversight, and traceability to only try to get into the high risk set. The thing is that I've been talking during the whole session about RisCanvi in the past, because RisCanvi is nowadays not in use. They are studying it in order to try to put it into that set, into the high risk set. Will they achieve it? I don't really know. I see it difficult, but someone in the room could think, okay, but why aren't we trying to comply in any other way? Why only using the AI Act? That's a good question, and that's also something I asked myself a year ago. And I tried somehow to do the same experimentation with ISO 42001, which is the one of artificial intelligence systems. But it would even be impossible also to get that certification, that quality certification for the system as it is. So presumption of conformity could never be either invoked. So what did we do in order to try to make this explainable? We used Marilyn Bello et al.'s article. Paco provided me about this article. And we tried to somehow split that black box into different explainability layers. We decided to set 3 layers here: the algorithmic layer, using SHAP, for example, in order to get which of the variables were the ones having more weight in the decision-taking moment. So the technical staff was aware and could see the reasoning behind that decision. Then we thought about the human-centered layer in order to give those prison professionals, lawyers, judges, everyone involved, any other stakeholder involved, adaptability, usefulness, and interactivity with the system so they could enjoy about the benefits of it, knowing the reason of the answers. And then we had the social layer in order to try to clearly and fairly, of course, give the inmate information they could understand to make changes and to act in consequence to try to get those privileges. But this is not the final part of it, because that seems to be one static action to be taken. But the thing is that, as Paco previously mentioned lots of days, explainability and trustworthy is not the thing of one day. It's not checking into a list once. So we also borrowed Paco's article. I always borrow Paco's articles. And we required somehow RisCanvi to stay always in a loop, in a governance loop. How? Splitting stakeholders into red and blue and giving them different responsibilities. The technical staff was responsible of the technical data drift, about risk representation, to refine explanation mechanisms, and to adapt new data and priorities depending on the social movements or in the society's evolution. And then we decided that prison guards, judges, psychologists, everyone had to assess under stability of the information they were getting, to review fairness and legitimacy, and to check legal or ethical alignment as soon as it was evolving the situation. So somehow with that we were trying to monitor, to review the system on the fly, to update it and to reassess those inmates which tasks were unfair in the moment the system was being used. But well, I'm almost getting into the final part of my presentation, and I want to go a step backwards and somehow forget a bit about RisCanvi, because this is also in order for you to know on how this work achieved. We achieved to do this in a really simple way because we were people from really different areas, and we knew, Jesus knew a lot of philosophy, Dorleta knew a lot of information about social science. The thing here is that it would have been impossible without those perspectives. So as soon as, as mature the AI gets, we are going to start to see synergies between different learning concepts, learning paths. For example, we published our paper here on Oier and Society in the Springer magazine, but there are many others. It exists AI and Law, Big Data and Society, Technology and Society. We are in a moment in which AI has got that mature that we need people who tries to challenge it, but with other perspectives, with other ideas. So, this is my little key message here. I want somehow to try to mix those kind of ideas to get new works really easily somehow. And I want to end up my presentation with the phrase you have here. It's the phrase we used at the end of our paper also, because AI is not only about doing a system that works well and deploying it, and that's all. AI nowadays changes lives and generates lots of consequences, socially speaking. So we as developers would have to somehow do that kind of internal exercise and think that when a person's future hangs in the balance, leaving the last word to a machine cannot grasp human vulnerability. I may leave scars too deep in society. We have to somehow be aware that anything we do at work, at home, wherever, will have consequences. And sometimes we forget about that. And I keep open to any question anyone has, and thank you for listening.
Thank you very much. Oier, please, question. 1, 2, 3.
Okay, so my question is, here what you do with RisCanvi is a post-mortem, like something went wrong, you know it, and then you propose how to fix the problem. Now, in the situation that this algorithm was still running and somebody were to audit, for example, they will check whether they comply or not with human oversight. And still they can go and say, no, we have a human in the loop, a person checking that models make correct decisions. Here you appoint that only a really small percentage of the decisions were overridden by humans, and that meant that people still say, like, do not understand the model and they're just accepting whatever. But also, maybe the person, if they were asked that person, like, are you truly understanding the model? And they will just say, no, the model has a really good accuracy and there is no problem with it. And so how do you detect that they are complying in an audit with human oversight in this situation?
Okay, let me ask you a question. If you only have one answer, I mean high or low, and you get that as valid, are you challenging the model? Do you know the reason behind that answer? If you are enough consist to show with SHAP, for example, okay, this is yes because this person killed 2 people. This is a high-risk person. Then you have an evidence behind that can prove that the system is doing their work well. But if you don't have in neither that, that idea or that number, you can never say. So you cannot challenge the system. You cannot answer. You cannot justify your decision.
Okay, so in that case, the auditor will ask, even if you agree with the machine, you will need further evidence.
Of course.
To say, okay.
Yeah, I mean, the AI Act says that you have to get sufficient transparency of the model when you want to deploy it, which is okay. But you have first to determine what's sufficiently transparent and then act in consequence. For example, here, sufficiently transparent could be getting the reason, for example, the ranking of the variables ordered in the probability in order to get the target, for example.
Yeah. Okay, so but in this case, they use, if I remember well, a logistic regression, which is one of the even considered interpretable models because it's a simple model. So wouldn't that be enough for the institution to say, no, the model is interpretable by design, so then it's not necessary of anything else?
As always, in bureaucracy, you need to prove it. You need a log. You need a reason. You need to justify yourself, not only in technology, in life. Nuri, you were going to tell me something.
My question, thank you so much. My question was, when you mentioned that there were, you had a slide with the inputs, and there were some obvious problems with those inputs. And I wanted to know if you know or anybody knows who came up with this inputs and how, what did they base their decision?
We only know that those variables came from a pool that was set by the developers in 2009, and we know nothing more than that. Because we only found auditing reports on the internet. I mean, we didn't have the information given by the Catalonians prison system or whatever. But yeah, I mean, what sounded weird to me was that, okay, let's use as protected attributes gender, nationality. But then, if I live close to the prison, I will be targeted as high risk, for example.
It seemed like they picked the obvious one, but we think it's just an arbitrary decision. Probably they just grab a whole bunch of.
I would say it was a conscious decision. Okay. I guess I would say that person had something in mind to think that was relevant. Although for me, there's no chance to see that relevant.
Yeah, I agree with you. I was just wondering if there was some research behind this or some reason behind it. You just said this is what we're doing and that's it. There was
publicly at least, and a year ago when we did this, no.
Makes sense. Thank you.
Thank you. According to your question, I want to say I don't think it's good to use this kind of qualification, but as far as I know, it's proven that one of the main, not the reason, but triggers for teenagers' violence is different parent roles. That has proven in psychology. So maybe that's the reason of some of the. I'm not saying that that's good, but maybe they had a reason based on something. That was not my question, just a comment. I want to say that thank you. I really liked your presentation. I think it's very
More
important.
than last year's?
Sure. This year you will gonna be the winner. You would be the winner, not last year.
I don't need any other backup.
No, but I think that it's so important the message that you said at the end, because as you said, AI we use it in our daily lives, and it can be so important. For example, if it changed human lives. So all of us in this room, I guess, as AI expert, I think we have to go outside and not stay in our office and collaborate with people in order to do AI for good. That's just a comment, and congratulations for you. But I have some questions. They are just for my curiosity. It's okay, don't worry, Oier. You said in 2 times the percentage of cases in which someone, a judge, I guess, changed the output of the algorithm in order to take the decision, right?
Yeah, they
you said
can
that
override.
3% or something like that.
Yeah.
But do you have any insight about the distribution of the outputs?
No.
You don't, because
was
they are no.
It was neither said. I mean, we only
Really?
knew, because look, this was, this started because we found a report on the internet of an auditing that Ethicas INC did.
Oh, wow.
And they were saying that, but the thing is that the judge is not the only one overriding the decision anyone could do. But the thing is that as nobody could justify why they didn't do it.
Yeah, but I was wondering because maybe the vast majority of the times risk can be set the low risk. So because it's not the same to give privilege to someone that doesn't deserve it, that not giving privileges to someone who deserves it. So maybe if RisCanvi was biases in that
RisCanvi
sense?
was more, RisCanvi was lax in order to give in order to try not to get risks, not to get unnecessary risks.
Okay, so it was...
So it was maybe targeting someone who was doing good things in order to get a permit to go outside for days, but it was saying, okay, no, this person is high risk.
So maybe as a default it said no, so okay, that's worse in my opinion.
Yeah, I mean,
yeah. I don't know about law, but in my opinion this is worse. And the final question for me, you said that they stopped using RisCanvi. When and do you know why? So because of the new laws, or
when? I'll tell you when, and it's when the AI Act started to begin. I think it was during 2021.
So it was forced to stop working. It wasn't because of
I'm not sure, because the AI Act
organization.
didn't enter by force in law, but it's true that it may be casualty. I don't know.
I don't think
but,
so.
Well, maybe also the report Ethicas did was like a way of criticizing the system, and that also made it stop. But it's neither written anywhere.
And do you know if they are trying to adjust this RisCanvi in order to be used as
far as I know, yes.
They are trying to. And do they contact you because of your paper? Because you are trying the same thing?
No.
No. Maybe you can call them.
No.
Okay. Any other questions? No?
Thank you very much.
You're welcome, my pleasure.
Well, we start immediately. I think so, no? Emily? You prepare your laptop. Well, we have the second part now with the presentation of Torsten, the second part.
You're welcome.